Hello guys, this is Saeed Mohammed Wakas. The topic which I'm going to discuss today is related to the plumbing system complete designing. Here is the course content. As you can see here, there are total 14 topics. Among that, first 10 topics are covered in this video, and the remaining 4 from 11 to 14 will be covered in the future uploaded videos. So first topic is water distribution system design using booster pump as a source of supply, and then second is pump head calculation using pipe flow expert software. Then hot water heater capacity calculation selection for individual and central heating system. Then water supply system demand calculation using water supply fixture unit method. Drainage system pipe sizing, drainage vent pipe sizing, and then hot water recirculation system design, pipe sizing, and pump head and capacity calculation. Then stormwater and combined sanitary drainage system design. Then chilled drinking water system design calculation, and then water supply hot and cold water pipe sizing calculation. So these 10 are covered in this video, and the remaining 4 like LPG tank sizing and selection using spreadsheet will be covered in the future videos. And swimming pool design calculation will also be covered in the future videos. Some pump sump pump calculation, some pit sizing calculation will also be covered in the future. And the last one is high-rise building water supply design calculation using spreadsheet, and this calculation will include main water tank, portable water tank capacity calculation, then gray water tank capacity calculation, treated water tank capacity calculation, then roof water tank capacity calculation and roof treated water tank capacity calculation, booster pump, transfer pump, and gray water pump capacity and head calculation will be covered in this topic. So all of the spreadsheets and software which I have used in the video, if you want to get access to the material, all you have to do is you just have to click the join button on the channel to get access to the material. You will take the membership and get access to the material based on your selected level. And in some countries membership is not available, YouTube membership is not available, so in that case you can proceed through PayPal or you can send an email address is given in the video description. So let's go to these topics one by one and discuss them. Hello friends, today I'm going to discuss the water distribution system design using booster pump as a source of supply, and this is the Excel sheet which I'm going to use for that purpose. You can see here, and there are other tables which I'm going to use in here. You can see the hydraulic tables also, and this is the example which we are going to cover in this session. So as you can see that we have a water service main line, and this is from the street main. If you see that the building information, it's a 16-story building, so I have write 16-story in here, and the street pressure we need to write here. So this street pressure, how you will get this one? You need to get this from the local authority of your area. Normally they are keeping the record how much is the street pressure, so you need to write in here. So let's say the local authority reported the street pressure is 45 psi in our area. So now the next thing over here, if you see here, this is the street main, and this is the piping which we took from the street main, that is water service line. And then we have a booster pump in here, and this is the suction of the booster pump, this is the discharge of the booster pump. And then from here, this point, we have taken the hot water heater supply, and this one is supplying hot water, and then this one is supplying cold water. And you can see that we have risers, different risers here. This is the riser 1 represented at section H, and riser 3 represented by section B, riser 4 represented by section C, and riser 5 represented by A, riser 2 is represented by F. So I just divided the each riser and section by sections. You can see here, this is A section, this is B, C section, this is B, and then this is section E, this is section D, this is section G, and then this is section I. I have divided this into different section in order, because we need to calculate the pipe sizes for each section, and we need to calculate the demand for each section. So the next thing we have to check here is the highest fixture outlet. So highest fixture outlet is 180 feet above the pump level. So we need to write this one in here because later we have to calculate the static pressure for the highest outlet. That's why we have write this thing here. So next thing is you have to check the highest outlet pressure requirement. Since the highest outlet which we use is the water closet and it's a flush valve operated water closet, so based on this we have to write the highest outlet pressure requirement. If you see the note in here, that is system, if the system is a flush tank operated, 8 to 15 psi we have to use the operating pressure, and if the system is a flush valve operated we have to use 15 to 25 psi. Since our case we said that water closet is a flush valve operated, so we have used 20 psi. This second case, 15 to 25 psi we can use, so we have used 20 psi in here. If you can join the channel membership, you can get access to the Excel sheet, MEP softwares, MEP books. You can see the channel membership link is given in the video description. You can click join button to get access to Excel sheet. Whatever the level you select, you will get material accordingly. If you have any thing you want to know before taking the membership, you can contact on the email address given in the video description. Even after taking the membership, you can ask things on the same email address mentioned in the video description. So if you join the channel membership, you can get access to Excel sheets, softwares, MEP books, depending on what level you have selected for the membership. So next thing we have to check the length of run to the farthest and highest fixture. So we need to write that length in here. So you have to go to your drawing and you have to mark the lengths of each section, riser and everything. So since we know that our water closet is the highest and the furthest outlet, so up to that outlet we have to check the length and we have to write in here. Let's say we got 350 feet is the length of run to the furthest, and the highest fixture is 350 feet. We have to write in here. This is called DLR, that is developed length of run. Develop length of run, DLR. Then material, this is also very important. So based on material, these hydraulic tables are prepared. You can see here from table 14-1 through 14-12. There are total 12 tables I have used here for sizing. So material for water service into the building, that is a copper K tubing. So if you see here, this is water service, this is the street main, and this one we are talking about, this is of type K copper tubing, material for water service into the building, this copper K. And if you see the other one, material for the water distribution system within the building, is type L copper tubing. So from pump discharge within the building, the piping is of type L copper tubing. So next thing we have here is uniform friction head loss. So we are going to use uniform friction head loss in order to calculate the hot and cold water pipe sizing, and we need to keep two things in mind while we do the sizing of the cold water and hot water pipe sizing. That one is one is the uniform friction head loss, which we set over here, this one, uniform friction head loss, and the second is the velocity. Velocity has a very prime importance for domestic hot and cold water supply system design. So if you see the note over here, maximum recommended velocity for domestic cold water supply pipe sizing is 8 feet per second. And for the hot water supply, maximum recommended velocity is 4 to 5 feet per second. So we are going to use 5 feet per second limitation in a case of hot water supply pipe sizing, and 8 feet per second in a case of cold water supply pipe sizing. So if you are going for higher velocities, if you are going to design your system on higher velocities, which is not recommended, you will have problems of noise, water hammer, cavitation, So that's why you need to follow this velocity recommendation, because we don't want to create any noise issue, cavitation, and water hammer. So we need to keep these velocities in mind. So we are talking about uniform friction head loss. Uniform friction head loss, normally we are taking 4 psi per 100 foot to 10 psi per 100 foot. So we have taken 6 psi per 100 foot over here, which is like most economical design is like 5 to 6 psi per 100 foot. So we have used 6 psi per 100 foot. So as you are changing this uniform friction head loss, if you move to 10 psi per 100 foot, then your pipe sizes will be smaller. That means less insulation will be used, smaller pipe insulation will be used. That means you are saving the cost on the piping and insulation as well, but you are increasing the head pump head will be increased if you increase the friction head loss. So let's say if I'm going to change this to 10 psi per 100 foot, you will see that pump head loss will be changed. There will be more pump head loss. Let's say this change is to 10 and pump head loss is increased. There is 115.4 psi. So more power will be used by the pump. So let's change back to 6 psi per 100 foot. Now the next thing which we have to use over here is PRV installed at the pump side. So there we have a PRV installed at the pump side. So obviously there will be a lot of fittings over here also, like maybe there will be some drain cock or something, and there will be a water meter here. So you need to add these values in here also. I added only PRV over here, and this PRV, pressure loss or head loss, I got this from manufacturer or supplier of this PRV. So I need to add this value here, 5 psi. If we have water meter over here, we need to add the water meter head loss here also. So next thing we have to add here is the static pressure for the highest outlet. So since we know that our highest outlet is 180 feet above the pump level, so now we need to calculate the static pressure for the highest outlet. We know that 1 feet is equal to 0.433 psi. So static pressure for the highest outlet is equal to 180 feet into 0.433. In order to convert this into psi, it will be 77.94 psi. Now next thing is the equivalent length of run. Equivalent length of run for this system. Equivalent length of run, it will be the sum of straight piping length, which you can see here, straight piping length, plus valves and the fittings used in this system. So since we don't know the sizes of the pipe, so what we do, we use this note. We are going to use a thumb rule, that is 50% of developed length will be considered as a friction loss for the fittings and the valve. This is a thumb rule. So we know that total developed length for the straight pipe of the fitting is 350 feet. We are going to add 50% of this 350 as a friction loss for the valve and the fittings. So how much our equivalent length of run will be? 350 into 1.5. So total 525 feet is the equivalent length of run. Now the last one over here is the friction head loss. How did we get this friction head loss? Friction head loss you have to get just simply multiplying your equivalent length of run with the uniform friction head loss. Uniform friction head loss is 6 psi per 100 foot and equivalent length of run is 525 feet. So if you multiply 525 with 0.06, you will get 31.5 psi friction head loss. And what is this friction head loss? This friction head loss is due to the straight pipe length plus fittings and the valves in your system here. So the friction head loss is 31.5 psi. Now the total initial pressure, it will be the sum of A, B, C and D. I have write A here, this one, B, C and D. So we need to sum up all these to get the total initial pressure requirement. So total initial required pressure is 134.4 psi. So now we know that street pressure reported is 45 psi. But in a case of peak demand, you will not be you will not get this 45 psi, maybe 5 to 10 psi less. So it is a good practice to take 5 to 10 psi less than reported pressure by the local authority. So I'm going to subtract 5 psi from this reported street pressure in a case of peak demand. So here it will be 40 psi. Now we can easily calculate the pump head, how much the pump head will be. So how we'll get the pump head? We need to this total required initial pressure minus suction pressure at the street main. So if you subtract the suction pressure from the street main to the initial pressure requirement, you will get the pump head. So that means pump head is 94.4 psi, and if you want to convert this into feet, so you will get 218 feet is the pump head here. So if you see over here, the total water supply fixture units which we calculated here, which I will tell you later. Let me just calculate the pump head and total capacity. So the total water supply fixture unit which we calculated here is 4840 fixture unit at this point. 4840 you can see here. So 4840 fixture unit, we need to calculate the pump capacity. We calculated the head, but we need to calculate the demand GPM for this one. So 4840 fixture units. So 4840 fixture units, I will go to this table. If you see the conversion of fixture unit to equivalent GPM, this is for the flush tank, this is for the flush valves. So if you note that after 1000 fixture units, values are same for flush tank and the flush valves. So our case, we have to check for 4840 fixture units. So if you go for 4000 we have and 5000 we have, so we will apply the interpolation formula to get the exact value of the GPM at 4840. So this is the interpolation table which I have. This is a formula which I am going to use, interpolation formula, to get the exact value. So we have 4000 fixture units and we have 5000 fixture unit, and we need to calculate GPM at 4840. So as I'm applying all the values, you will see the GPM calculated here. So we know that for how much GPM we have at 4000 and how much GPM we have at 5000. So go here, 4000 how much GPM, 525, and 5000 we have 593. So 525 and 593. So 525 and 593, it will calculate at 4840. So how much GPM calculated at 4840? 582 GPM. That's how I write 582 GPM, and reference table is 13-4 which I use here, this one. So this is how you can calculate the booster pump head as well as demand. So now we will proceed towards the hot and cold water demand. So after demand, we have to calculate the pipe sizes for the hot water as well as cold water. So here I used only water supply demand calculation for riser 4, which is represented by section C. So in the same way which I'm telling you now, you have to calculate the water supply demand for other risers and other sections of the building. So this is the riser 4 which I'm going to calculate right now, demand calculation. So in riser 4, I got there's a flush, there's a water closet of flush valve types, and urinals we have, and the lavatory we have. So we have to write all the fixtures for each riser and section one by one, and then we have to go for number of fixtures. So how many water closet I have? 55 water closets, 15 urinals wall hung, and 42 lavatories. So now we have to calculate the hot water fixture unit and total hot water fixture unit. Now we have to calculate cold water fixture unit and total cold water fixture units, and then combined hot and cold water fixture units. So number of fixtures, I write 55 here. Now I have to get the value of each water closet. So I'll go to this table, demand weight of fixtures in fixture units. So we have a water closet now, and 16-story office building, and this we considered as and we know that it's a flush valve operated water closet. Flush valve operated water closet. So occupancy is public, flush valve operated, and you see that cold, there is no cold water connection on water closets, that's why there is no value in here. So hot, there's no water, there is no connection of hot water, so that's why no value here. So we have only cold water point in the water closet. So value of fixture unit is 10 in a case of water closet with a flush valve, and total fixture unit value is 10. So we are going to write for cold water fixture unit is 10 value, and combined it's also 10. Combined water supply fixture unit value is also 10. So how we will get the total cold water fixture unit? We just need to multiply number of fixture with each fixture unit value. So we'll get the total cold water fixture unit value. So in the same way you have to go for urinals, and how we will get the total water supply fixture unit? We know that 10 value we have calculated here. 10 value, you can see that combined for a total value of fixture unit is 10. So we have write 10 here. So it's the same, 10 into 55, that is 550 total fixture units. So now I'm going to show you for the laboratory as well. Total 42 laboratories we have, and each total 42 laboratories we have here, and in the laboratory we have both hot water as well as cold water connection. So we need to write value for the hot and cold water. So we'll go here in our table 13-3. Now we have to check for laboratory. So laboratory, if you see here, this one is the laboratory, but this is a private, and this laboratory is public. So we are going to use this one, public laboratory. So if you see here, the hot water is 1.5, cold water is 1.5, and total fixture unit value is 2. So we will write here hot is 1.5 fixture unit, cold each fixture unit is 1.5, and combined is 2. So 1.5 into 42, you will get the total hot water fixture unit, that is 63, and 42 into 1.5, that is cold water fixture unit. 42 number of fixture unit into each cold water fixture unit is 1.5, so total is 63 also as well. And if you see the combined, we have 2, so 42 into 2, you will get 84 total fixture units. The reason is, so if you see the total hot water fixture unit at riser 4 section C is 63, and total cold water fixture unit at riser 4 is 688 fixture units. So same, if we have right here hot water 63 fixture unit, cold water fixture units are 688 fixture units at riser 4 or section C. And the reason why I have calculated the total water supply fixture unit, because when we do the sizing for this section, that is from pump discharge up till this point where the connection is taken off to the hot water heater, so this line and the water service main will be sized based on total water supply fixture unit values. That is, this is only for riser 4. You need to calculate for every riser and sum up. You need to calculate for every riser this for total water supply fixture unit value, and write in here it is, that is 4840 fixture unit. So you need to size this piping and water service main based on this total water supply fixture unit value, that is 4840 fixture unit. And from this point you have to do the sizing for each section and riser based on the fixture units. That is, cold water fixture unit is the total cold water fixture unit at this point is 4730, and total hot water fixture units are 345. So if you see here, if you sum up the water supply fixture units up till this point, let's check the cold water fixture units. So this riser 5 or section A is 1376 plus we have 688 here and 430 cold water fixture units here, that is 2494 at this point, and then we have to some cold water 860 here, 860 plus 2494, that is 3354. So we have 3354 cold water fixture unit at this point. Now the last one is riser 1, that is 1376 fixture unit plus 1376. So total cold water supply fixture units are 4730 fixture unit, you can see here up till this point. Same way you have to calculate the hot water, it will be 345 fixture units. But as I told you, from this point you have to calculate the pipe sizes and GPM demand based on total GPA, total water supply fixture unit. Just like we calculate for riser 4, you have to calculate for riser 3, 2, 1 and then sum up, and it will be 4840 fixture units. So now next step is we have to go for the cold and hot water pipe sizing, and I'm going to use the hydraulic tables to calculate the cold and hot water pipe sizing. You can see that these hydraulic tables, there are total 12 hydraulic tables which I'm going to use. So let's go to the calculation sheet and let me show you for any riser to calculate the pipe size. So let's check for riser 5, which is represented by section A. You can see that riser 5 represented by section A, and how many cold water supply fixture units we have here, 1376. I'm not going to calculate for all risers demand. The way I have shown you for riser 4 represented by section C, same way you have to calculate the demand for each riser and each section. Otherwise video will be much longer, that's why you have to calculate. This is just a procedure to show you how you can calculate. So riser 5A fixture units, cold water supply fixture units are 1376. Now we need to calculate the demand at this point. So as I told you how we need to convert this fixture unit into demand GPM. So how we'll get this one, I have used the interpolation table as I shown you before. So 1376, this is a cold water, so 1376, so we have 1250 and we have 1500. So this one is for the flush tank and this is for the flush valve. So our this riser contain the flush this water closets with flush valve system operated, so we are going to follow this column, the flush valve. So 1250 demand is 240 GPM and 1500 demand is 267 GPM. So 240 and 267, we have to write here GPM, and this one is 1250 and this one is 1500, and we need to check fixture unit value at 1376. So fixture unit value we have 1376, we need to check the demand. So how much is the calculated demand at 1376 fixture unit? This is the interpolation formula, so which I have used here to get the exact value of the demand, that is 254 GPM. So now we know the demand at 1376 fixture unit. So now we need to calculate the pipe size. So now I have to check the pipe size. So the table which I have used here is 14-9 as a reference table to calculate this pipe size of 4 inches. Now I will tell you how did I get this pipe size of 4 inches. So demand calculated here is 254 GPM. 254 GPM. If you see here 254 GPM. So since if you remember that in the beginning I said that material for water service into the building is copper K and distribution system inside the building is L. So we have to check this L copper tubing, 254 GPM. So this is the L copper tubing. and 254 GPM. If you see that 240 GPM, we have 260 GPM, we don't have 254 GPM, so we will interpolate the value for 254 GPM. If you see that 240 GPM value is this is the velocity column and this is the head loss column for copper L tubing. So 240 GPM velocity is 6.42 and 260 GPM velocity is 6.95. So we will use interpolation formula to get the value at 254. So 240 and 260 we have 6.42 velocity and 6.95. 6.42 and 6.95 at 240 GPM, and 260 GPM we need to calculate at 254 GPM. So how much is the velocity calculated at 254 GPM? That is 6.79 feet per second. 6.79 feet per second, as you can see here. So since this 6.79 feet per second is less than 8 feet per second, which we set here in the beginning, so the pipe size which we selected 4 inches here is okay. We can use 4 inches pipe size. Now we have to calculate the head loss also. We use the uniform head loss of 6 psi per 100 foot. So now we need to calculate the head loss also at this pipe segment or riser 5, which is represented by section A. See, same way we have to calculate the head loss. So we will just write the GPM here, interpolation table, and we calculate the head loss. We'll go here and now we'll calculate the head loss. 240 and 260. 240 copper L tubing. How much is the head loss? 1.9 psi per 100 foot, and 260 head loss is 2.1. So 1.9 and 2.1. 1.9 and 2.1. So calculated head loss is 2.04 psi per 100 foot. So 2.04 psi per 100 foot. So this is how you have to use hydraulic table to get the pipe size for cold water pipe sizing. So let's go for another riser. Let's check for this riser 3 plus 4 plus 5, which is represented by E, as you can see here in the drawing. This pipe segment which we are going to calculate now, this is riser 5A, this is 4, and this is 3. So at this point it will be the sum of section A, B and C, which is represented by, and also as well as D. So D is basically the sum of D is basically the sum of this riser 3 and 4 is represented by D. So if you see that total fixture units at this point section E, it will be, so if you see the sum of 3 and 4 riser is cold water supply fixture unit 430 and 688. That is 1118, which is written here, 1118 represented by D, and then we have to add this 5A cold water supply fixture unit 1376 plus 1376, so 2494. So total for cold water supply fixture unit at section E is 2494. So we need to calculate demand first, 2494, in order to get the pipe size at this section, which is represented by E. So you can see here, I just sum up this, and in order to get the value, so 3 plus 4 is represented by D. So and we get the value of total fixture unit is 2494. Now we need to convert this into demand GPM. So how we'll do this one? So we will I will use the interpolation table again. 2494, and if we go here and we will check, we have 2250 and 2500. So 2250 fixture unit, 2500 fixture unit, the value is 348 and 375. 348 and 375. So 2250 we have 348 and 2500 we have 375. So how much is the GPM calculated if we have a fixture unit of 2494? GPM calculated is using interpolation formula 374 GPM. So we have right here 374 GPM. So demand is done. Now we have to calculate the pipe size again, and then velocity, and then head loss. We need to confirm the velocity should be less than 8 feet per second. So now we need to calculate the pipe size first for 374 GPM. Reference table we use is 14-10. So this is the 14-10 table, and how much GPM we set? 374 GPM. So 374 GPM. So one thing I need to tell you first, if you see that 374 GPM is also available in here, but if you move to the copper L tubing and check the velocity is 9.36 at 350 and 10.70 at 400. So 374 is also available in here, but if you see the velocity is higher than recommended velocity, it exceeds the limit. That's why we are not using this 4-inch pipe size. Head loss, although the head loss is okay, but velocity is exceeding, so we are not going to select 4-inch pipe size. That's why we have selected 5-inch pipe size, table 14-10. So if we go here and we check 350 and 400, so we need to check at 374 GPM. So 350 copper L, type L copper, velocity is 6.01, and 400 6.87. 6.01, 6.87. This one is at 350, this one is at 400, and we need to check at 374. So 374, if we check the velocity calculated is 6.42 feet per second using the interpolation formula. So we have right here 6.42 feet per second. Now we need to calculate the head loss as well. Same way, we go to 14-10 table. 350 head loss is 1.3, 400 head loss is 1.7. 1.3 and 1.7. Head loss is 1.49 psi per 100 foot at 374 GPM. So 1.49 psi per 100 foot at, so if you notice that the velocity 6.42 is less than 8 feet per second, and the head loss is 1.49 psi per 100 foot. So both values are less than our recommended values which we said in the beginning. So the 5-inch pipe size selected for 374 GPM is correct here. So now in the same way you have to calculate the pipe sizes for other sections. Now let's check for the hot water pipe sizing, how you will calculate the hot water supply pipe size. Let's take one example for this one. So we are going to calculate the hot water pipe size for section G. So if you see that this is the section G, and hot water supply fixture units at section G are 249 fixture units. So we have 249 fixture units over here. Now we need to calculate the GPM for this hot water supply pipe sizing. So how we'll get the GPM for this one? So same, we have to use 13-4 table to get the GPM. This table we have to use for fixture unit to GPM. So fixture unit over here are 249. This is for the flush tank, this is for the flush valves. 249. So 225 and 250 over here. But at this point, for hot water pipe sizing, you have to use the flush tanks, not the flush valves column, because we don't have a water closet and urinals included in the hot water piping system. So we have to use flush tank over here this time for the hot water piping. pipe sizing. So we have 225 and 250, that is 70 and 75 GPM. 70 and 75. 225 and 250. 225, 70 GPM, 250, we have 75 GPM. We need to check at 249 fixture unit how much the GPM value. So it's same 75 GPM, so we are going to use 75 GPM here as well. So here we have used 74 GPM, so 74, 75, so we will change this to 75 GPM. So we are going to use 75 GPM here. Now we need to check the pipe size at this GPM demand. So how much pipe size, hot pipe size will be. So table which I used here is reference 14-7. So I'm going to use this table. Demand is 75 GPM. So we have a demand of 70 GPM here, and copper L, type L copper. If you see 70, we have 4.70, and the 80 we have 5.37. 70 we have 4.70 velocity, and 80 we have 5.37. Four point 5.37. $70 and $80, and we need to check at how much GPM. 75 GPM. So velocity is 5.04 GPM, 5.04 feet per second, sorry, 5.04 feet per second. So recommended velocity is 5 feet per second for hot water system. As we said, it is 5.04, is almost 5 feet per second. So we can change the size to 3 inches, but it's okay to use 2.5 inches because it's almost 5 feet per second. So that's why we have used 2.5 inches pipe size in here. So in the same way, you have to calculate the pipe sizes for all other sections. You have to calculate the pipe sizes for the sections, the as I have written here in the table. So the last thing I have to tell you over here is you have to calculate the pipe size for this section from booster pump discharge up to the point where connection is taken off to the hot water heater. So this will be sized based on total water supply fixture unit, as I mentioned you earlier. So total water supply fixture units over here are 4840 fixture units. So I need to do the pipe sizing for 4840 fixture units. So let's go to the calculation sheet. We calculated the total water supply fixture units are 4840. Let's get, we already know the demand at this point is 582 GPM. So how, let's get the size. Let's get the size of this pipe size. Let's get the pipe size for this demand. So this time I'm going to check the table, hydraulic table. Over here it's a 5-inch table, and 5-inch table, if you check the demand here is 550 and 600. So 550, we have 550. If we check the velocity is copper L tubing, since this is again inside the building, this so we have to use copper type L copper. So 550, the velocity is 9.45 feet per second, and 600 velocity is 10.3 feet per second. So again this velocity is higher than recommended 8 feet per second, so we are not going to use 5-inch pipe size. So we'll go to the next table, 6 inches, and then check the demand 550 and 600. 550 and 600 type L copper, velocity is 6.57 at 550 and 7.17 at 600. So 6.57, and let's interpolate and get the exact value at 582. So 6.57 and 7.17. 7.17. This is at 550 GPM fixture units. Sorry, this value we have to check the velocity. So 550 we have 6.57 velocity, and 600 we have 7.17 velocity. We need to check at 582 GPM. So how much it will be? So velocity calculated at 582 GPM is 6.95. So 6.95 is the velocity calculated in here, feet per second. So the velocity calculated here is 6.95 feet per second at 4840 fixture unit, and with the pipe size of, how much is the pipe size we selected here is 6 inches. So 6-inch pipe size. So 6 inches pipe size. So this pipe segment from discharge, booster pump discharge up to this point, it will be 6 inches. So same water supply fixture unit you will have here, 4840 fixture unit. So same pipe size we can use in here. So this is how you can design your water supply system using a booster pump as a source of supply. So I hope you guys learned something from this video. For more videos, keep watching my channel. Don't forget to subscribe and don't forget to press the bell icon. And one more thing before ending this video session, if you can join the channel membership, you can get access to the Excel sheet, MAP softwares, MAP books. You can see the channel membership link is given in the video description. You can click join button to get access to Excel sheet. Whatever the level you select, you will get material accordingly. If you have any thing you want to know before taking the membership, you can contact on the email address given in the video description. Even after taking the membership, you can ask things on the same email address mentioned in the video description. So if you join the channel membership, you can get access to Excel sheets, softwares, MAP books, depending on what level you have selected for the membership. So this is the end of this session. Hello guys, this is Syed Mohammad Waqas. The topic which I am gonna discuss today is related to the pump head calculation using Pipe Flow Expert software. As you can see that there I have opened Pipe Flow Expert software. Before starting drawing the pipes on the grid, let me tell you something about this software. As you can see that this is the drawing grid area on which we are going to draw the pipes and placing pumps, flow control valves and tanks. And this is the area where you can see the pipes, tanks and their properties. And this is the toolbar at the top. You can see that there you can add fittings, components, pipes, add demand pressure, add demand flow, everything you can add from here. So let's start drawing the pipes, and we'll discuss these things one by one. So first of all, I'm gonna take the tank from here. I'm gonna place one tank here, and second tank I'm gonna place in here, and third one I'm gonna place in here. So what I'm gonna do basically is I'm gonna draw the pipes, and we have to pump the water from this tank to this one and this one. So first of all, you have to select the tank, and then you can see in here the surface pressure. So I'm gonna keep this open to the atmosphere, so I will keep this surface pressure 0. And liquid level, we have to write the liquid level, how much is the liquid level in this tank. So let me change the units. So you can change the units also by just going to the units and change from imperial to metric or metric to imperial. So I'm gonna change this to imperial. So I'm gonna give the level, liquid level, to 30 feet in this tank, and bottom elevation I will give 0 for this tank 1, and this is the tank 2, and this is tank 3. So tank 2, I'm gonna place this one at same 0. I will keep surface pressure, and liquid level I will keep for tank 2 is 15 feet, and bottom elevation for this tank 2 I'm gonna keep this, let's say, 50 feet. And same for the third tank, you have to give the surface pressure open to the atmosphere, so I'll keep 0. And liquid level, let's say the liquid level in this tank is 25 feet, and the bottom elevation of this tank 3, let's say it's 70 feet. So I am done with the elevations and everything. So let's draw the pipe. Here you can see that add pipes, you can draw the pipes from there. So I'm gonna draw a pipe from this tank. So once you draw the pipe, first pipe segment, then it will ask that by default it's schedule 40 pipe, and length is that much, diameter is that much, and roughness is that. But if you want to change these values, you can just select yes now, or you can change the pipe values. Or if you want to change it later, you can do it also later by just selecting no. So I'm gonna change it now, so I will select yes. So here you can change the pipe material, diameter, length, everything in here. So let's if you want to change the pipe material, you just go to the material, and here you see that all the materials are already there in this software. The best thing about this software is you can find all the materials, fittings, their K values in this software, and it will calculate automatically the pump head. So right now schedule 40 pipe is selected in here, steel. So I'm gonna keep the same, and pipe size selected is 4 inches. So instead of 4 inches, so I'm gonna change this to 2.5 inches. So it depends, whatever the pipe size you have calculated, according to that you have to select the pipe size in pump head calculation. So I will keep the same material, and I will change the diameter from here. This is for steel schedule 40, you can see in here. And I will change the pipe size to, let's say, 2.5 inches. If you just select this use selected size, it will be changed, and you have to save to the pipe, and then okay. Also, if you want to change the length of this segment, you can change the length. You can see that this is represented by P1. You can change the length from here. So let's say we keep this to 10 feet, and you can see the pipe diameter, we already changed this one to 2.5 inches. So let's draw more pipes. Now I will connect this pipe with the third tank over here. So as you can see that I have draw the pipe segments in here. So what we basically doing in here is we are supplying water from this tank, first tank, to the second tank and to the third tank. So we're gonna place one pump in here that will supply the water from this tank to the tank 2 and tank 3. So now I'm gonna add pump and the fittings. So let's say we calculate the total demand for these two tanks is 200 GPM. So what I'm gonna do is I'm gonna let's say, and we got 80 GPM for this tank, and we got 120 GPM for this tank. So in order to control the flow at this tank, 80 GPM and 120 GPM for this one, I'm gonna use one flow control valve either here or here to control the flow across these lines, so that I will get total, if we have a total 200 GPM in here, 80 will flow here and 120 GPM will flow there. So first of all, I'm gonna place a pump of 200 GPM. So you just select the pump from here and just click the pipe here, and you can place the pump in here. So if you want to change the by default data, you can change in here also. Just yes, it will open this dialog box, so you can check this one. The pump is in here. There are three types of pump which you can select in here. You can select this one, fixed flow rate set to that much, and fixed head increase or fixed speed. So if I know the demand, total demand for these two tanks, let's say it's 200 GPM, so I'm gonna use this fixed flow rate. So pump will produce 200 GPM fixed flow rate. So as per demand, I'm gonna select this fixed flow rate set to, I will change the unit to US gallons per minute. Let's say it's 200. So I will select this one and it's saved to the pipe. And then what you have to do, let's change the elevation also at these nodes. So we know that this elevation is 0, same as this one. This one, let's say change the elevation, just select the node and change the elevation from here, elevation of the joint. So let's say this one is 50 feet. So this tank elevation, this one also I will keep the same 50, and this one also 50. So also this tank is placed at 70 feet elevation, so I will keep this joint 70 feet. And if you want to change the length also of this pipe segment, you can change the length also. So just select the pipe. Let's say we'll change this one to 40 feet and change this one to, let's say, 30 feet. And this one, let's say I will change to 20 feet. This one 10 feet. Okay, let's keep this one 10 feet. So now I'm gonna place the fittings like elbows, tees, everything in there. So how we can place them, just go select the pipe segment and go to add fittings. Just select this one and select the pipe segment in here. You can place the fitting in here. So as you can see that this pipe segment, we will have I will keep one gate valve in here. So you can see that this is 1 inch size in here. So we have selected 2.5 inches. So this is 2.5 inches. Still schedule 40 pipe you can see in here. So I'm gonna place one gate valve in here. So there I have a gate valve, this one 2.5 inches. Just select this one, add to the pipe section, and after that there will be an elbow at this point, at this node. So I'm gonna place one elbow also, that is standard bend 2.5 inches. There's a K value 0.54. K value is also in here, you can see. Just add to the pipe segment, then standard bend will be added, that is elbow. And one more thing I will add in here is pipe entry sharp edged, this one from tank to the pipe. This fitting I'm gonna add. So just add to the pipe, and you can see the total K value for these three fittings is 1.18. After that just save it. So you can see that the fittings are available in here. So after that I'm gonna add one T at this point. You can see that there's a T connection in here, so I'm gonna add a T in here. So just select the pipe, 2.5 inches, pipe size is same. There's a branch T connection, you can see that there's a branch T connection in here. So I'm gonna select a branch T in here, 2.5 inches, and you can see that this is the through T and this is the branch T. So I'm gonna select the branch T, 2.5 inches, add to the pipe. K value is 1.08. Just save it. Then again we have to, there is no fitting away here, so I'm gonna add some fittings here also. So just select the add fittings, select the pipe segment. Here I'm gonna add one gate valve here. 2.5 inch gate valve. So just select 2.5 inch gate valve, add to the pipe, and there's one more fitting which I'm gonna add in here. Pipe exit to the container, so or tank. So I'm gonna select this fitting at this point. So just select this one and add to the pipe, save it. So you can see that the fitting is added in here. And one more fitting we have to add in here, that is elbow at this node. So there will be an elbow, so I'm gonna add one elbow in here also. So just select the fittings again, select this pipe segment, and select standard bend. This one, you select this one, add to the pipe, save it. So these fittings are already added in there. So now I'm gonna add fittings here also. So I'm gonna select this pipe, I'm gonna add the fittings in here. So just select the add fittings here, select the pipe segment. Here I'm gonna add one gate valve here. Also, if you see, I will add some elbows, like one elbow at this point and one elbow at this point. So total two elbows I will add, 2.5 inches. So standard bend, add to the pipe and change the quantity to 2. And gate valve, 2.5 inch, add to the pipe. So one gate valve in here. And one more thing, we have to add the pipe exit to the container at this point. There will be a fitting pipe exit to the tank, this one. So I will add this one also, add to the pipe. Total K value is 2.22. Just save it. I have to add the flow control valve for this one. We said that total demand, let's say we got total demand is 200 GPM at for this pump. So you can see that. So and we, let's say we calculated the 80 GPM for this tank 2 and 120 GPM for tank 3. So we have to place a flow control valve so that 80 GPM will flow to this path and 120 GPM will flow to this path. So I'm gonna add some component in here. So you can see that add control valve. So just select this one and select the pipe segment where you want to place the flow control valve. Select this one and give it a name of FCV, that is flow control valve. And the flow which we are going to limit in here is 80 GPM. Just select OK. So that means 80 GPM will flow this way and 120 GPM will flow this way. This is a constant pump flow, so it will gonna give 80 here and 120 here. So we are almost done with placing the pipes, components, everything. So what we have to do next is we have to just in order to generate the results or in order to calculate the pump head, you can see that calculate button in here. You just have to press calculate and it will generate the results. There's a dialog box will appear. You can see that the network was solved successfully and solution values are displayed on the drawing. Or you can see that in here pump head is 91.257 feet calculated, and low pressure at any node is this much, and highest pressure at any node is this much. Let's close this one and view the drawings, view the results on this drawing area. You can, if you hover your pointer to any of the pipe segment, you can check the results like flow and velocity, length, diameter, start elevation, end elevation, start pressure, end pressure, everything you can see in here. Even at the tank you can see that liquid level, elevation, pressure, everything is shown in here. Also on the drawing, if you see that this is representing in red color, this is representing in dark green, and this one is in light green, and you can see the color of the pipe flow rate in US GPM. Red means 200 GPM, so this is 200 GPM coming from this way. Then dark green is like 80 GPM this way, and this is the flow control valve that is supplying 80 GPM to this tank 2, and in the middle you see that light green color that's flowing this way, that means around 120 GPM this way. Or you can see that this is F means flow 120 GPM, this is 120 GPM, this is F means 80 GPM, and this F is 200 GPM. So you can also go back to your log. You can view the results in Excel sheet also by clicking this one, or you can also create a PDF report. Just click this one, and whatever the data you need you can select and check the PDF report. So you can also change the company name, whatever your company name is you can write in here. You can write the project name, and you can choose whatever the data you want to check in the pipe, whatever the data you want to check in the node, and you want to check in the energy data. So let's say I will remove the mass flow, and let me check the friction loss in here. So after selection is done, just click the create PDF report. It will generate the report of your results. So this is the drawing, you can see that, and this is the fluid data. You can see in here we have used H2O water, 68 degrees Fahrenheit. So you can also change the fluid by just going back in here, go to redesign, go to the fluid, and you can change the fluid in here. You can see that a lot of fluids are available in here, like ammonia, butane, and propane, water. By just clicking the all fluid, it will show the gases also in here, all the gases, everything in there. If you just click the liquids, it will give you only liquids in here. So you can see that we have selected water, 68 degrees Fahrenheit temperature. So by default we have selected the water. So let's move back to our report, PDF report, and you can see that the pump data is available in here. You can see that pump in and outflow which we have selected is 200 GPM, velocity is 13.402 at the main pipe, and suction pressure you can see that 12.6 psi, and discharge pressure is 52.08 psi, and pump head you can see that 91.257 feet head is the pump head for our system. This system pump head calculated is 91 feet head, and net positive suction head required is not known. You have to check this one when you will select the pump from the supplier, and net positive suction head available calculated is 62.29 feet. So you can also check the pipe data. This is the pipe segments. You can see pipe 1 2 3 4 5 6 7, and the material which we use 2.5-inch steel schedule 40 pipe. Internal diameter is shown in here, pipe roughness is shown, total length of the each pipe segment is shown in here, total K value, friction loss coefficient values for each pipe segment is shown in here. So whatever the fittings and you have used in your pipe segments, its K value, loss coefficients are shown in here. The best thing about this software is you can have all the fittings K values for all the materials is available in here. So you can just select the material, accordingly you have to select your pipe fittings, and it will automatically take the friction loss coefficient K values. So you can see the velocity also in each pipe segment. You can check the entry pressure, exit pressure, and friction loss. So this is how you can read your pump head data. So it's very easy to calculate the pump head using this pipe flow expert software. So I hope you guys learned something from this video. For more videos, keep watching my channel. Don't forget to subscribe, and don't forget to press the bell icon. Thank you. Hello friends, this is Saeed Muhammad Wakas. The topic which I'm going to discuss today is related to hot water heater capacity calculation and selection. So the first sheet here is related to the individual hot water heater capacity calculation selection, and the second spreadsheet here is related to the central hot water heater capacity calculation and selection. You can see here. So individual hot water heater supplying hot water to single or multiple spaces without any recirculation system. But here we have a central hot water heater which is supplying hot water to multiple spaces within the building and have large capacity, and we have a hot water recirculation system as well. So therefore in this central hot water heating system we will calculate the central hot water heater capacity, storage tank capacity, as well as we will calculate the circulation pump flow as well as head. So the source of heat in the central hot water heating system could be solar, boiler, or heat pumps. So primary source of heat are these three which I mentioned here. Of course there will be a secondary source of heat would be attached to the storage tank, and that is electric power heater that is attached to the hot water storage tank. In case primary power is failed, there will be a secondary source of power will be there for hot water system, and that will be electric backup power heater. So let's get started with the first spreadsheet, that is individual hot water heater capacity calculation and selection. So as you can see here that the calculation will be according to the type of building and fixture unit method. So it is very important to select the type of the building here, because this table here, the demand mentioned here as well as demand factor and storage capacity factor, all of these are depending on type of the building which you select from here. There are several type of the building you can see here: apartment, club, gym, hotel, hospital, industrial, office building, private, residential, and many more in here. So it depends on what type of building you will select. If I select the gym, the demand will be changed, demand factor will be changed. You can see here demand factor, storage capacity, everything will be changed. Like if I select industrial, it will be changed as well, and if I select the private residential, it will be changed as well. So let's say I'm going to select individual hot water heater for an apartment here, apartment in the building. So first and this table is extracted from ASHRAE application handbook chapter 45 table 9, this table. So this table means the demand, all of the demand mentioned here, the demand factor and storage capacity factors. So it depends on type of the building which you select here. So first step, you have to go to the drawing and you have to count the number of fixture needed hot water in your space. So you have to go and count the number of fixture need hot water. Let's say the fixture type and number of fixtures here. So let's say the lavatory which are private in the apartment. So the private lavatory we have two, and you have to check this from the drawing. So you have to check the bathtub. If it, let's say it's 1, dishwasher 1, foot basin 1, kitchen sink 1, laundry 1, and shower 2. So all you need to do is you have to put the values here in the quantity, and it will calculate the total gallons per hour GPH. So private lavatory, you can see here we have 2, and then we have bathtub 1, then we have dishwasher 1, foot basin 1, and then kitchen sink we have 1, laundry we have 1, and shower we have 2. So once I put all the values in here, it will calculate the gallons per hour for each fixture. So total is calculated in here, which is the sum of all the fixtures here. So total GPH is calculated 132 gallons per hour. So now we have to apply the demand factor in here. As I told you, this demand factor is depend on type of the building which you have selected in here. So for apartment it's 0.3, so you just need to multiply this demand with 0.3 demand factor and you will get probable maximum demand is 39.6. so heater recoil capacity is same as probable maximum demand, which is calculated in here, that is 39.6. now the storage capacity factor, this again depends on type of the building which you have selected here. Storage capacity factor, so storage tank capacity in the gallons we need to calculate in here. We simply multiply this probable maximum demand with this storage capacity factor. Here you can see that, and we will calculate the storage tank capacity in gallons. So needed storage tank capacity in gallons is 27.72. gallons. So if you need in liter, you simply need to apply the conversion factor and you will get the storage tank capacity in liters. So now we know the storage hot water heater storage tank capacity in liters, so we can select the hot water heater from the suppliers catalog. So you just have to go to the approved suppliers catalog, and then you will, let's say I have one here, that is Zenith water heater catalog. Let's say this is the approved catalog, which approved supplier catalog which I have in here. So I will select from this one. So as you can see here, these are the horizontal wall ceiling mount hot water heater, and these are the capacities you can see here. So we have 100, we have 100, 120. So these are available in the standard capacities, and the one which we calculated here is 105. So 120 is there, so we are going to select 120 liters capacity in here, and the standard power, if you see, is 2 kilowatt. So we'll select 120 liter capacity with 2 kilowatt power. So we have to write in here 120, which we select, and power is 2 kilowatt. So as I write in here, so water heater selection is done here. So selected hot heater storage capacity in liters is 120 and power is 2 kilowatt. So this is how you can do for the individual hot water heater system. So let's go to the central hot water heater calculation here. So same calculation will be made according to the type of the building and fixture unit methods. Here you have three things. First is the type of the building, second is the type of the pipe will be used, and the type of the means insulation, it's insulated or not insulated, you have to write here, and the type of the pipe. So again, it depends on type of the building. These table values, this demand factors, and this capacity factor depends on type of the building which you select from here. So there are a lot of available here. If you select the hotel, this demand will be changed, as well as demand factor and storage capacity factor will be changed. So same for school, if you select the school or hospital, it will be changed as well. So let's say I'm going to select for office building, and pipe I'm going to use the hot water pipes is insulated or not insulated. This is very important to select in here, because this table, which is extracted from ASPE code, so here the values heat loss per foot of the pipe, it depends if you have pipes insulated or uninsulated. Insulated, if you have like fiberglass insulation, half-inch fiberglass insulation, you can select here the insulated. As I select insulated, the values will be changed. Depend on the if I have selected the insulated or non-insulated pipe. So let's say I am selected the non-insulated pipe, I don't apply any insulation. If you have insulation, you can select insulated pipe, and these table values will be changed accordingly. So again, you have a type of pipe used. So there are different pipes available here: schedule 40 steel, brass, and type K copper. So again, these values Q loss per foot of the pipe depends on the material which you select from the top. So it is important to select the correct material from here. So let's say I'm going to select for type K copper here, office building, non-insulated pipe. So if you have insulated pipe, you don't have to worry about if I have insulated pipe here, I don't have to worry about the type of the pipe which I'm going to use here. So let's move to the next step. Again, same thing. First of all, you have to write the number of fixture. You have to count the fixture from the drawing, and then you have to write the quantities in here. It will calculate the demand in gallons per hour. So let's say I have laboratories in the office building that are 15. Let's make this non-insulated. And laboratories, we have 15 in the office building, and we have a kitchen sink 10, we have pantries 10, and service sinks 10. So let's write the quantities here in the table. Again, the source is same, ASHRAE application handbook for this table, chapter 45, table 9. So let's me write the laboratories. For public laboratories, 15 laboratories we have. Then we have kitchen sink, we have 10. Pantry sink we have 10, and service sink we have 10. So once I write all the quantities in here based on my drawing, so I will calculate the gallons per hour here, which is the sum of all the fixtures. So 590 here. So in order to get the probable maximum demand, I need to multiply this demand factor with this gallons per hour demand. So I will multiply 590 with 0.3. I will get the probable maximum demand is 177. So heater coil capacity is same as the probable maximum demand, that is 177. Now the storage capacity factor is 2 for this office building. So storage capacity factor is 2. So storage tank capacity in gallons will be, you simply need to multiply this probable maximum demand with this storage capacity factor. You will get 354 gallons storage capacity for this office building. If you need to convert this into liters, simply apply the conversion factor. You will get the capacity in liters. So again, you have to go to the approved supply catalogs and select this storage tank, hot water heater storage tank. So next step is I have to calculate the pump flow and the head for recirculation system, hot water recirculation system. So as I told you, this table is extracted from ASP code table 17-1. It is important to compute the values to proceed for pump head and capacity calculation for recirculation system. So I have write all the pipes from the drawings in here, whatever I have used in the project for hot water system. So I have write in here. So piping length I have write in here from the drawing as well. Now this Q loss, that the heat loss per foot of the pipe, it depends on this pipe material is insulated or not, or type of the pipe which you have selected in here. So now we have to calculate the heat loss in BTUs per hour. Since this value is in meters, we need to convert this into foot. So that's why we have multiplied this with 3.28 in here in order to convert from meter to feet. And we just need to multiply this 80 into 3.28 into 15. We'll get the total loss in BTUs per hour. So same way you have to do for all the piping you have used in your project. So and you have to calculate the heat loss in BTUs per hour for each piping length. So once you calculate for all the pipings in your project, you have to write total loss in BTUs per hour in here for hot water network, which is the sum from top to the bottom. See, that is, so we got total 67,174 BTUs per hour heat loss. So for each 10,000 BTUs per hour need 1 GPM. So we need to add 1 GPM for each 10,000 BTUs per hour. So we calculate here is 67,174 BTUs per hour. So required GPM for heat loss makeup pump will be total heat loss in the system, that is this value 67,174 divided by 10,000. So required GPM for the heat loss makeup pump will be 6.7 GPM. So this is the capacity. So now we have to calculate the pump head as well. For in order to calculate the pump head, we have to check the furthest pipe length for supply as well as return to get the pump head. And since we have a loss in the straight pipe length as well as the fitting, so we have to compute the loss for the straight pipe length as well as fittings to get the pump head. So in order to get the pump head, you need to 1.5 into uniform friction head loss, uniform friction loss into total piping length. Why I multiply this with 1.5? Let me tell you first uniform friction loss first, and then I will tell you 1.5. Why I multiply with 1.5? It is recommended to use 4 foot per 100 foot to 6 foot per 100 foot uniform friction head loss. It is recommended. So if you have seen my previous videos, I have used the 4 foot per 100 foot uniform friction head loss. So same I have used in here, 4 foot per 100 foot uh, of the uniform friction loss. And why I multiply this 1.5 to compute the losses for the straight pipe length and fittings. So if you don't know the friction loss for the fittings, it is a thumb rule to add 50% of the straight piping length of friction losses for the fittings. So 50% and 1, it will be 1.5 total. So that's why I multiply with 1.5. So 1.5 into 4 by 100 into total pipe length. So total pipe length, as I told you, it is the furthest pipe length supply and return from the source of supply to the furthest outlet. So from the drawing you have to check the furthest pipe length, and you have to write in here. I have write 70 and convert this into feet here as well. So pump head is equal to, calculated in here by adding or putting all the values in here, 1.5 into 4 divided by 100 into pipe length is 229.61. So after putting all the values you get the pump head 13.8 feet head. If you want to convert this into psi, just multiply with 0.433, you will get the pump head in psi, that is 5.97 psi. So now we can well, now we know the storage tank capacity for central hot water heater system is 354 gallons storage tank is needed. And hot water circulation pump selection is also done. The flow which we calculate here is 6.7 gpm, and the head which we have calculated here is 5.97 psi. So this is how you can do the hot water heater capacity calculation, storage tank capacity calculation and selection. So I hope you guys learned something from this video. For more videos, keep watching my channel. Don't forget to subscribe. Thank you. Hello guys, this is Sayyid Muhammad Waqas. The topic which I'm going to discuss today is related to the total water supply demand calculation for a building. If you remember, about 1 month ago I made a video related to hot water and cold water pipe sizing. In that video I did not explain how you can calculate the water supply demand. So in this video I'm going to show you how you can do that by using a water supply fixture unit method, that is WSFU, and by using International Plumbing Code IPC and UPC, that is Uniform Plumbing Code. But before proceeding towards the calculation, I want to tell you one more thing. In my next video I'm gonna discuss about the water distribution pipe sizing with one more complicated example. As you can see that we have risers in here also. In the previous example for water supply and hot water and cold water pipe sizing, it was not complicated. So in my next video I'm going to use this complicated example. You can see the risers are also included in here, so you will learn more in this video. And we are going to do the pipe sizing for the main service lines, and we are going to do for water supply distribution piping, and we're going to go for risers also. So let's move back to our main topic. So let's say we have an office building, and we have a number of fixtures are described in here. Like water closet, we have flush type, and 60 water closets are in there. And urinals, we have a wall hung type, and a flush valve type is used in there. So 12 urinals, and lavatory we have 40. So it depends on number of fixtures which you have in your drawing. You have to write the total number of fixtures in here. So second thing, you have to, since we are using water supply fixture unit method, so we have to write the fixture unit value associated with each fixture. So here are the tables and charts which I'm gonna use. So first fixture is water closet, and number of fixtures are 60. So there is no hot water required for this one, so we'll go for cold water fixture units and total water fixture units. So if you see over here, and occupancy is also matters. Since this is an office building, so we're gonna select this public space instead of this private space. And type of supply, we know that this is a flush valve instead of flush tank. So water closet, public type, flush valve. You see the cold water fixture unit required are 10 and total water supply fixture units are also 10. So move back here to our Excel sheet and write cold water fixture units are 10 and combined water supply fixture units are also 10. So since we know that one fixture unit requires 10, so 60 fixture unit you need to multiply 60 into 10, that is 600. Again same thing, 60 fixture units in here and combined water supply fixture unit value is 10, so 600 is the total water supply fixture unit. And urinals we have 12. This is a wall hung flush valve type. Move back to our chart and tables. So here you can find stall or wall urinals and stall or wall urinals, one with the flush valve, another with the flush tank. So since we have used the flush valve type, so we are gonna use this value. So cold water required is 5 fixture units and total is also 5. So same way we have to write cold 5 and total is also 5. Again you need to multiply this number of fixture with cold water fixture unit to get the total water supply fixture unit here for cold water, and total water supply fixture units are also 5 by 12, that is 60. And the last fixture we have here is the lavatory, and lavatory required both hot and cold water. So move back to our tables and charts and find the lavatory in here, and you can see that this lavatory is private and we are looking for public. So you can see that this is lavatory. Since we have an office building, that's why I'm going to use public occupancy. So lavatory, public, faucet type. You can see the hot water fixture unit is 1.5, cold is also 1.5, and total fixture unit required are 2. So hot and cold are 1.5 and total are 2. So we can write hot water fixture units are 1.5 and cold water is also 1.5 and total 2. So simply you need to multiply this fixture unit with number of fixtures, this fixture unit with number of fixtures, and this fixture unit with number of fixtures to get this total cold water fixture unit, total water supply fixture units, and total hot water fixture units. So this is the demand which we calculated here is the intermittent demand, that is a non-continuous demand. It's not used all the times, its frequency of use is different, it's not used as continuous demand. This is a non-continuous demand. We need to add the continuous demand to the non-continuous demand if continuous demand is available, but before that we need to convert our fixture unit values into the GPM. So since we know that total hot water fixture unit is 60, so we have write 60 in here, and total cold water fixture unit, it is a sum of these three, that is 720 fixture units, and combined water supply fixture unit we have in here is 740 fixture units, that is the sum of this one. Now we have to convert this fixture unit value into GPM, so we are gonna use the table in here. So this is the table. You can use this chart as well as this table to convert this fixture unit to equivalent GPM. So first is a hot water, that is 60 fixture units. So hot water 60 fixture units for the lavatory. So we are going to use this there we have two columns, flush tanks and flush valves. So we have 60 fixture unit. For flush tank it's 32 GPM. 60 fixture unit is 32 GPM. So we're gonna write 32 GPM in here, and then we have to get the value for cold water fixture unit and combined fixture units value also. So total water supply fixture unit are 720 in here. So we have to go back, but cold water, if you see that we have a flush valve type for this one, so we are going to use flush valve column in here. Whatever the valve you are using in there, you have to follow that column. So 720 fixture units. So we don't have 720, we have 500 and 750. So if you go for the second column, this is flush valve. So we have 720, so I'm gonna write approximate value in here, that is 100. Let's say we are gonna write 174 value in between them, and we check for total water supply fixture unit value, or combined water supply fixture unit is 740. So 740, if you go in there and let's say approximate value, we will get between 500 and 750 is fixed. Let's say we get the GPM of 177 GPM. You can do interpolation to get the exact value. So right now I'm just writing the approximate value, that is 177 GPM. So this is our intermittent demand which we calculated in here. So now we have to add this demand with the continuous demand. If you have any continuous demand, you have to add this with intermittent demand. So let's say we have 2 hose babes there, and we have to go back to our tables and chart to get the fixture unit value for this hose babe. So as you can see that demand at individual fixtures and required pressure. If you see, this one is the flow rate GPM, this is the fixture, and this is the pressure. So this is the hose babe as you can see over here, and the GPM required is 5 GPM. So we have 5 GPM required in here. So 2 hose babes, it will be 10 GPM. And the second continuous demand is air conditioning makeup water. So this value you have to get from the HVAC design engineer. So how much is the required GPM for the air conditioning water makeup? So let's say we get this value 30 GPM. So we just need to add these two values to get the total continuous demand. So TCD is the total continuous demand, that is 10 plus 30 equal to 40 GPM. And then you can see that hot water demand, here hot water demand we already calculated, that is 32 GPM in here. And the cold water demand, you need to add this continuous demand also in the cold water demand, because this water supplied here for the continuous demand is also normal or cold water. There is no hot water required in here. That's why we did not add any continuous demand to our hot water demand. It's simply 32 GPM. But for cold water demand, we need to add this continuous demand also, because this also required normal or cold water, hose babes and air conditioning water makeup equipments. So total cold water demand will be, that is cold water demand we calculated here 174, for intermediate demand, and continuous is 40. So 174 plus 40 equal to 214 GPM. And total water demand required here is 217, that is 177 is the total water demand here, plus continuous demand, that is 40. So total water demand required is 217 GPM. So reason why we have calculated hot water demand, cold water demand and total water demand, because if you move back to over this example which we are going to discuss in the next video. So here if you see, this is our service main. So we are gonna this service main pipe sizing based on our total water demand required. So we have to do sizing based on total water supply demand required, that is this value. So if you go from here, this is our pump, that is a booster pump, this is the suction and this is the discharge. So from service main to the point of connection to the, this is our hot water heater, from service main to the point of connection to the hot water heater, we have to do the sizing of this water supply piping based on this GPM. This is just an example to show you That's why we have calculated this total water supply demand. But after that you have this hot water piping in here, so you have to do this hot water piping based on this hot water demand, because here you have hot water supply, this is hot water supply, and then this is your cold water supply. After this point of connection you have this cold water supply, so you have to do the sizing of this cold water supply piping based on this cold water demand. That's why we have calculated this hot water demand, cold water demand, and total water demand. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe and don't forget to press the bell icon. Thank you. Hello guys, this is Syed Mohammed Waqas. The topic which I am going to discuss today is related to the drainage pipe sizing. So there I have prepared an Excel sheet. As you can see over here, there's a lot of tables which I'm going to use to calculate the drainage pipe size. And this is the drawing for the 9-story building. As you can see over here, it's given here, and we are going to calculate the pipe size for each branch. As you can see, the sections are given as A, B, C, D, E, F, G, H, I, and then stack J, and then run out K, and then we have run out again M. So this is the drawing which we are going to use and to calculate the drainage pipe size. Before starting calculation, I want to give one small message to you guys. If any one of you interested in PhD from Canada, then you guys should visit this channel, Vagabond TV. This channel is related to the PhD in Canada. There you find a lot of videos related to PhD in Canada. So this is really helpful for you guys if you are interested in PhD from Canada. So please subscribe this channel. So let's move back to our topic. So as you can see that there I have a drawing for 9-story buildings, and we have divided each branch. We have given the name of each branch as section A, B, C, D, E, F, G, H, and I. And this vertical stack is represented by J, this run out is represented by K, or offset is represented by K, and then again this vertical stack is represented by L, and this run out is represented by M. So as you can see that I have prepared this table. In branch A, how many fixture unit we have? As you can see over here, we have 70 fixture units. So you have to understand first what is the fixture unit. Fixture unit, if you remember that we have used the fixture unit in water supply pipe sizing. That time it was called water supply fixture unit, and here we are going to do for drainage system. That's why it's called drainage fixture units. So fixture unit basically depends on 3 factors, that is rate of discharge, time of operation, and frequency of use of fixture. So based on these factors, these tables prepared by ASPE, that is American Society of Plumbing Engineers, IPC International Plumbing Code, and UPC Uniform Plumbing Codes. So based on these factors, these tables developed by these IPC, UPC, and ASPE. So I took this table from ASPE, that is American Society of Plumbing Engineers. So based on this table, I'm gonna do the sizing of drainage piping. And as you can see that we have horizontal branch sections given as A, B, C, D is mentioned here in the Excel sheet, and we are going to calculate the pipe diameter. And then we have a vertical stack, that is J, and this vertical stack is represented by L, vertical stack J and L. And then we have offset or run out, that is represented by K and represented by M, K and M. And the list of the fixtures in each branch section is given over here. So for example, branch A, we have water closet, urinal, lavatory, kitchen sink, shower, domestic, bathtub, laundry, floor drain, and bidet. So according to that, we have write the fixture unit value from the table 6.2. So this is the table, fixture unit per fixture or the group. So from this fixture we have taken value and we have given it over here. So for example, water closet, you can see the drainage fixture unit value is how much. You can see the water closet over here. So since we are using the valve operated water closet here, so we are going to use this value 6. So water closet drainage fixture unit value is 6, so you can write 6 here. So in the same way you have to write the drainage fixture unit value for each and every fixture, and then number of fixtures given in branch A for water closet is 5, urinal we have 2, and lavatory we have 2. So you need to multiply number of fixture with the individual fixture unit drainage fixture unit value, and you will get the total drainage fixture unit value for the water closet in the branch A. So total drainage fixture unit value given for branch A, it will be the sum of all these fixtures. It will be the sum of all these fixtures. So 30 for the water closet, 8 for the urinals. You need to sum up all of these drainage fixture unit value to get the total drainage fixture unit value in the branch A. So total drainage fixture unit value is the sum of all these, that is 70. Same way you have to write the drainage fixture unit values over here in this column for the branch B by seeing the which fixture unit is connected to the branch B. So you have to write the fixture unit values in here and then multiply with the number of fixture unit to get the total drainage fixture unit value. So this is how you have to do for all branches, that is A, B, C, D, E, F, G, H and I up till here. So first we are going to calculate the branch pipe size for branch A, B, C, D, E, F, G, H and I. And second we are going to calculate this stack pipe size represented by J, and then we calculate the pipe size for this offset runout K, and then again vertical stack pipe L, and then again this offset or runout M. So first we are going to calculate the pipe size for this branch A. Since we have 70 fixture unit connected to this branch A by using, and this table 6.4 we are going 6-4 is going to be used for fixture unit loads for sanitary branches. So we are going to use this table 6-4 to calculate this branch pipe size A for all of these branches. So we have 70 fixture unit over here. So as you can see, the total fixture unit we have 70 is in between 20 and 160 and in between 3 and 4 inches. So we will go for 160 on the higher side. So 160 on the higher side, so we'll get the pipe size is 4 inches. So we'll write 4 inch pipe size. And again branch B, that is 90 fixture units. 90 fixture units again come between same table 6-4 we'll use. It's in between 20 and 160, that is we'll go for the higher value, that is 4 inches. So in the same way you have to calculate for this 120 fixture unit branch C. 120 fixture unit is also between 20 and 160, so we'll go for the higher side, again 4 inches. So D has 90 fixture unit, we already calculated for B, it will be same as D, that is 4 inches. Now we'll calculate for the branch E, has 150 fixture unit load value, it's again less than 160, so we'll go for 160. It is in between 20 and we'll not go for 20, we'll go for 160, and pipe size is 4 inches. And then you can see the branch F has 180 fixture units. So 180 fixture unit, it is in between 160 and 360. So we'll go for the higher value 360. 360 we have 5 inch pipe diameter, so we're going to use 5 inch for section F. And then we have section branch G with 190 fixture unit. So in the same way you have to write for G, H and I. G is 190, 190 is also less than 360. We'll go for the higher value, that is 360 is 5 inches, and h is also 160. 160 is in bit 160 is here 4 inches, and then I, you can see, is 200 fixture units. 200 fixture unit is in between 160 and 360, so 360, that is 5 inches. Now we have to calculate the vertical stack pipe. As you can see over here, this is represented by J. So when you are calculating the vertical stack pipe size, you need to sum up all these branches fixture unit load, that is 70, 90, 120 and 90. That is equal to 370 fixture units. So 370 fixture units load will be on this vertical stack represented by J. Now to calculate the vertical stack pipe size, you need to use this table 6-3, that is maximum permissible fixture unit load for sanitary stacks. So this first column is for the, if we have a 3-story building or less than 3-story building, then we have to use this column. If you have more than 3-story building, then you have to use this third column. Since we have a 9-story building, so we are going to use this third column. So since we have 370 fixture units connected to this vertical stack J, so 370, these are the fixture unit values. 370 fixture unit, that means it is between 60 and 500. So obviously we'll go for the higher value, 500. So if you move to the left side, you will find the stack diameter is 4 inches to the 500 fixture unit value. But you need to check one more thing in the last column, that is total discharge in each branch interval fixture unit is 90. This condition should be satisfied, that total discharge in one branch interval should not exceed 90 fixture unit value. But if you go there, you find that this 70 is okay, 90 is okay, 90 is okay, but here we have 120 fixture unit value. So these branches connected to the stack J is not satisfying the condition of 90 fixture unit value. So this is exceeding with one branch interval. This branch has more than 90 fixture unit value, so we cannot take this value for 4-inch pipe size. So we need to increase the pipe size from 4 to 5 inches. So if you select this 5-inch pipe size, you can see in the last column we have total discharge in one branch interval is 200 fixture units. Since 200 fixture unit is the maximum in each branch interval, if you see over here, we have all branch interval less than 200, that is 70, 90, 120 and 90. So our condition is satisfied, so we can select this 5-inch pipe size for this vertical stack J. So this is 5 inches, and then we have to calculate this offset runout pipe size, and the slope which we used in our project is 1/8 inches per feet. So this K section or runout or offset is going to be sized based on the table 6-5, maximum permissible fixture unit load for sanitary building drains and runout from the stack. So this is a runout from the stack pipe, or it is also called offset. So how many fixture unit we have here? Same A, B, C, D. You need to sum up all these branches, that is 370 fixture unit over here. So 370 fixture unit with 1/8 inch slope, so 370 fixture units, it is in between 180 and 390. We'll go for the higher value, 390. So for 390 with 1/8 inch slope, you will find 5-inch pipe diameter. Even if you are using 1/4 inch slope, it will also be 370 will also be in between 216 and 480. Obviously we'll go for the higher value, 480. So same 5-inch pipe size. So since we have 1/8, so 5-inch pipe size we are going to use in here for this offset K. And then we have this vertical stack again representing by L. So here if you are calculating the pipe size for this vertical stack L, it will be the sum of all the fixture unit above offset and all the fixture unit below offset. This is the offset. Sum of branches above offset, sum of branches below offset, to get the size of this stack L. So we know that 370 here, and how much is here you can calculate. That is 370 plus branch E is 150, F is 180, and G is 190, H is 160, and I is 200. So total fixture unit value to calculate the size of this stack L is 1250 fixture unit. So as I told you, to calculate the stack pipe size we have to use this 6-3 table. Total fixture unit value for more than 3 story stack, more than 3 stories, we have to use this column because we have a 9-story building. So we have total fixture unit value is 1250. 1250 is in between 1100 and 1900. So obviously we'll go for the higher value, so we'll go for 1900. So for 1900 you can see that 6-inch pipe size. Same time we have to check the total discharge in one branch interval is 300 fixture unit. So each branch interval should not exceed 300 fixture unit value. So let's check and verify the condition. So maximum fixture unit in each branch interval is 200. So it is satisfied, this condition is satisfied that our each branch interval, that is total discharge in our each branch interval, is less than 350 fixture unit. We have a maximum of 200 fixture unit. So this condition is satisfied, so we can use easily this 6-inch pipe size for vertical stack L. And in the end we have to calculate this pipe size for this offset or runout represented by M. So total fixture unit value, it will be the sum of all branches from top to the bottom. We already know that is 1250 fixture unit. So this is runout or offset. As I told you that we have to use table 6-5 to calculate this offset pipe size that is going directly to the manhole, and total fixture unit value is 1250 and slope which we used is 1/8 inches. So 1250 is in between 700 and 1600. So obviously we go for the higher value 1600. So 1600 you can find the pipe diameter, that is 8 inches. So we can use 8-inch pipe size. Again, if you note over here that 1250 is coming in between them, so we'll go for 1920. If you have a slope of 1/4 inches, still pipe size will be 8 inches. So since in our project we use 1/8 inches, so it's the same, that is 8-inch pipe diameter. That value is coming between 700 and 1600, and our fixture unit value is 1250. So we are going to use 1600 and pipe diameter is 8 inches. So M is 8 inches. So this is how you can calculate your drainage pipe size by using the tables from ASPE, American Society of Plumbing Engineers, IPC and UPC, that is Uniform Plumbing Code. But again, I have to tell you one thing, that you have to follow the local codes of your area. For example, if you are working in India, you have to get the values from the local authorities. These tables you have to get from the local authorities, because every region has its own codes and standards developed by them. For example, if you're working in the Gulf region like UAE and Saudi Arabia, Bahrain, Qatar, you have to follow their standards. This is an international standard which I have discussed in here. So I hope you guys learn something from this video. For more videos, keep watching my channel and don't forget to subscribe and don't forget to press the bell icon. Thank you. Hello guys, this is Said Mohammad Waqas. The topic which I'm going to discuss today is related to the drainage vent pipe sizing. So there I have an Excel sheet as you can see here, and these are the tables which I'm going to use for drainage vent pipe sizing. So I'm going to discuss two examples here. This is the first example and this is the second example. So in the first example you can see that we have individual vent pipes which will do the sizing, and in the second example, this is the second example, you can see here if you see that we have the vent stacks that is A, B, C and D that are connected to the common vent header. This is our common vent header at the top of the vent stacks and then extended through the roof at one point. So this is the second example. So in first example, if you have noticed that this is the same example which I had used during the drainage soil stack pipe sizing. If you have not seen that video, I will give the link in the description below. You can watch it because this vent stack pipe size is related to the soil stack pipe size, so you must watch that video. And if you see that here we have vent stack that is represented by section B. Vent stack is represented by section B, and you can see that this is the dashed line representing the vent pipe, and this is our soil stack is represented by A. So this is our second vent pipe, you can see here represented by F in the dash lines, and this E is basically representing the soil stack. So when you are doing the vent pipe sizing, three things should be known. First is the soil stack pipe size, second is the drainage fixture units connected to that soil stack pipe, and third is the developed length. So these three things should be known before doing the vent pipe size calculation or before getting the vent pipe size. So what is developed length in here? So you need to understand the developed length first. So developed length is basically the length of the vent stack is measured from the point of connection to the drainage system at its base point. So this is the base point from here to the point of discharge at the outlet above roof. So from the base point of the drainage system to the point of discharge at the roof level. So this is our high roof level and this is our low roof level. Six story, you can see that we have a low roof level in here. So from this base point of the drainage system to the top of the roof level, this is representing the developed length. Before starting the vent pipe sizing, there is one announcement about the channel membership. If you join my channel membership, you can get access to all Excel sheets, relevant softwares and carrier air conditioning design handbook. So basically the membership on my channel has 3 levels. Membership link I will give in the video description, or you can go to my channel and click the join button. So let's start the pipe sizing with the first example. So this is for the first example, you can see that the section B here, as I said that vent stack is represented by section B. So I said that three things should be known to get the vent pipe size. So first is you have to check the soil stack pipe size. So I'm not gonna discuss the soil stack pipe size, how did we get this one. So for that purpose you should go for drainage system design or drainage pipe sizing video. I will give the link in the description below just to save the time. So I will proceed to the next step, that the connected drainage fixture units. So you can see that total connected drainage fixture units is how much: 90, 70, 120 and 50. So we have total 4 branches here, that is 90, 70, 120 and 50, total 330. So up till this point we have 330 fixture units connected here. So we write here 330 fixture units, and the develop length, which I said that from the base point, so we are talking about this vent pipe. So develop length is from the base point to the top of the roof level. So you can see that 10 feet, 10, 20, 30, 40, 50 and 55. So develop length is 55 here. So now we have to check the vent pipe size here. How much is the vent pipe size connected to the vent stack having, connected to the soil stack having size 5 inches. So we know that soil stack pipe size is 5 inches. Develop length is 55 and connected drainage fixture units are 330. So we're gonna use this table 9-1. We said that soil stack pipe size is 5 inches, and 330 fixture units. So 330 fixture units is in between 200 and 500. So we'll go for 500 higher value. And so before going this, let me tell you about this table. These pipe sizes 1/4, 1/2, 2 inches, these are basically vent pipe sizes. These are the connected drainage fixture units, and this is the soil stack pipe size. And in between we have these develop lengths. These are the develop lengths. So we know that 5-inch pipe size, soil stack pipe size, and 330 fixture unit will go for 500. And develop length is how much? 55. So 55 is in between 30 and 70. We'll go for higher value 70. So 70, you will check the pipe size is 3 inches. So vent stack pipe size is 3 inches. So we got 3-inch pipe size in here. So same way you have to check for the second one. That is second stack pipe is represented by F. You can see in here. So how many branches are connected to this stack F? So we need to include the branches above this run out. We need to add this one also. So 330 plus 160 plus 200 plus 230, and the last one is 170. So total drainage fixture units connected are 1090. 1090 we can write here. So again we have to check the develop length. How much is the develop length? Since this one is connected from the base point of the drainage system to the top of the roof level, this is onto the low roof level. So total develop length is 10 feet, 20, 30, 40, 50 and 55. So again 55 develop length here, and 1090 drainage fixture units. And again you have to check the connected soil stack pipe size. You can get that one if you see the video, drainage pipe sizing video. So we use the table 9-1 again. 1090 drainage fixture units, and soil stack pipe size is 6 inches and 55 is the develop length. So 6 inches with 1090 drainage fixture units, 6 inches and 1090 drainage fixture units. 1090 is between 960 and 1900, so we'll go for 1900. And develop length is 55, again between 20 and 70. We'll go for 70. Higher value, there is no 55, so we'll go for 70 and check the pipe size is 4 inches. Vent stack pipe size is 4 inches. So we have 4 inches here. So now I'm going to discuss the second example here. Here you can see that we have 4 vent stacks represented by A, B, C and D. These are connected to the common vent header. This is a common vent header and then extended to the roof. So we'll start from stack A. You can see here I have divided into different sections. Stack A, you can see that fixture units are 150 and develop length is 180. So 150 fixture units, 180 develop length. So we need to check the soil stack pipe size. So soil stack pipe size, and then we have to check the vent stack pipe size, and then we will check the header pipe size later. So first we check for the stack A, soil stack pipe size and vent stack pipe size. For this Section A. So first check the soil stack pipe size using the table 6-3. So we have 150 fixture units. 150 fixture units. Since we know that we have more than 3-story, so 150 fixture unit, we have to use this column. 150 is in between 60 and 500, so we'll go for 500 higher value, and we'll check the soil stack pipe size is 4 inches. So 4 inch. So now we have to check the vent stack pipe size. So we know that developed length is 180 feet, and we know that soil stack pipe size is 4 inches, and we know that drainage fixture unit connected are 150. So we use this table 9-1. So 180, 150 fixture units, 180 developed length. 150 fixture units, 4 inch pipe size. 150 fixture units, 100 and 200 is here, so we'll go for 200. And developed length is 180, is in between 90 and 250, so we'll go for the higher value 250 and check the vent pipe size is 3 inches. So vent pipe size is 3 inches. So next is A to B. This is the vent header, section A to B. So here we will check the header pipe size now. The developed length is now 180 plus 10 more, that is 190. So developed length is 190, 180 plus 10. This is the 10 feet. Drainage fixture units connected are same, that is 150, same. So 150 fixture units and 190 developed length. So 150 is, again we check the size for the soil stack is again 4 inches. So 4 inch pipe size and 150 fixture units and 190 developed length. 150 fixture units is in between 100 and 200, and 180 is the developed length is in between 190 is the developed length is between 90 and 250. You'll go for 250. Again pipe size is 3 inches. So header vent pipe size is 3 inches. Section A to B header pipe size is 3 inches vent pipe size. So now we'll go for stack B. 200 fixture units, 290 developed length. 200 fixture units, 290 developed length. Now we'll check for soil stack pipe size and vent stack pipe size. So 200 drainage fixture units. First check the soil stack pipe by using the table 6-3. So again, more than 3-story, 200 fixture unit is in between 60 and 500. So we'll go for higher value 500 and check the pipe size is 4 inches. So pipe size soil stack is 4 inches. Now check for the vent stack pipe size. So we know the soil stack pipe size is 4 inches. We know drainage fixture unit 200 and 290 is the developed length. Now we check the vent stack pipe size. So again we use table 9-1. So 4 inches, 200 fixture units and 290 developed length. So 290 developed length is in between 250 and 900. So we'll go for higher value 900 and check the vent pipe size is 4 inches. So this stack B vent pipe size will be 4 inches, this vent pipe. And then we'll go for header pipe size B to C. Now we'll check for header pipe size B to C, this one. So we know that the drainage fixture unit A to B is 150 and this stack B is 200. So 150 plus 200, it will be 350 for the point B to C. So you can see here 150 plus 200, that is 350 drainage fixture units. So now the developed length we can see here at point A to B, total developed length was 180 plus 10, that is 190 plus 40. 190 plus 40, that is 230. You can see here 190 plus 40, that is 230. So now we check the header pipe size B to C. So we know that drainage fixture unit 350. So first check the soil stack pipe size, how much it would be. So based on this we have to check header pipe size. So 350, if we check the, so again in between this, and we'll go for higher value 500, 4 inches pipe size. So 4 inches we have to check developed length 230 and 350 fixture units. 4 inches, 350 fixture units is in between them, so we'll go for the higher value 500, and developed length is 230. 230 is between 180 and 700. We'll go for higher value 700 and check the vent pipe size is 4 inches. So the header vent pipe size B to C is 4 inches. So now I'm gonna skip B to C, C to D. B to C is already done, so I'm gonna skip C to D and stack C just to save the time. So I'll go for the last one, stack D, 500 fixture units and 270 developed length. So 500 fixture units at stack D and 270 developed length. First check the soil stack pipe size for 500 fixture units. So again 6-3 table, 500 fixture units, soil stack pipe size is 4 inches. 4 inches, okay. And then we know that developed length is 270. You can see that here, developed length 270. So soil stack pipe size is 4 inches, 270 developed length, and 500 fixture units. So 4 inches, 500 fixture units, and 270 developed length is in between 180 and 700. We'll go for high value 700 and check the vent stack pipe size is 4 inches. That is 4 inches, you can see here. So now the last one is from D to the outlet. You can see that from D to the, this is the roof level extended up to the roof. So for total developed length will be how much? That is C to D. C to D it was 260. C to D it was 260 plus 40 plus 10. So 260 plus 40 plus 10, that is 310 total developed length. And fixture units, if you see that here 500 fixture units, here you can see that C to D fixture unit, which we calculated is 550. So 550 plus 500, it will be 1050 fixture units. So we know that developed length, we know that drainage fixture units, so we can calculate the vent header pipe size. So first check the soil stack pipe size, how much it would be on 1050 fixture units using table 6-3. So 1050 fixture unit is in between 500 and 1100. So this value 1100 we will take. So soil stack pipe size will be 5 inches. So 5 inches with 1050 drainage fixture units and 310 developed lengths. Let's check the header pipe size, vent header pipe size. So 5 inches, 1050, that is equal to almost 1100. So 5 inches soil stack pipe size, 1100 drainage fixture units, and developed length is 310. 310. So 310 is in between 200 and 700. So you will go for the higher value 700 and check the vent header pipe size is 5 inches. 5 inches. So you can see that this is the 5 inches. So this is how you can do the drainage vent pipe sizing. If you have the individual vents, or you have the vents that is connected to the common vent header. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe and don't forget to press the bell icon. Thank you. Hello guys, this is Sayyid Muhammad Waqas. I am back with another video. The topic which I am going to discuss today is related to the hot water recirculation system. And this topic is very important, so please make sure to watch the video all the way till end and don't forget to subscribe my channel. So let's start hot water recirculation system design. So as you can see that there I have prepared an Excel sheet and I have taken an example of 24-story building, and we're gonna design the hot water recirculation system for that 24-story building. So here I have a table also which I'm gonna use. So first thing you have to do here is you have to write your risers, all the risers in here which you have shown here in the figure. So as you can see that I have given the name for each riser, like riser 1, 2, 4, 3 and up till 11. And hot water piping is already shown here in the drawing, as you can see that. So if I will zoom and you guys can see, this is our water heater installed in the basement, and this is the hot water supply piping. This is the hot water supply piping from here, and if you see that this is going all the way up till 24 story, and then there's a recirculation piping, hot water recirculation piping, and this recirculation is going back into the heater. So we are going to design this recirculation lines. So we are going to design the risers, and we're going to design the main for recirculation system. And hot water piping is sizes are already mentioned in here. So if you remember that I have made a video on domestic hot water pipe sizing. So if you don't know how to do this hot water pipe sizing, you can go back to my channel and you can watch the video about domestic hot water pipe sizing. So I have to write all the risers in here, and main also. This is the risers and this is the main, from risers to one riser to another riser. That means this is the horizontal pipe. You can see that this is the horizontal pipe for recirculation, this one. So first you have to do is you have to write the hot water pipe sizes here, and the second thing you have here is hot water piping BTUs, loss per hour per unit length. So this is you have to write in here, and you have to write the length, and then hot water piping BTUs loss per hour based on this length, and then you have to calculate this hot water recirculation piping BTUs per hour, and in the end you have to calculate this GPM to overcome the heat losses. So first of all I'm gonna take main from heater to the heater to the riser 1. So as you can see that this is the heater which we have in here, and this is the hot water supply piping. You can see in here this, and size of this pipe is 4 inches, hot water supply pipe, and sizes for recirculation pipes are unknown, so we are going to calculate. So this hot water supply pipe size, you can see that it's 4 inches up till this point, and this point is riser 1, and then again you go over here and you will see the size is same, 4 inches, 4 inches, 4 inches, you can see here. So from this point 3, riser 3, size is changed to 3 inches, then you have 3 inches up till here, this point 14, riser 14. So after that your size is changed again to 2.5 inches. You can see here 2.5 inches, again 2.5 inches, and then here you have 2 inches. So if you see from main, from heater to riser 1, so heater to riser 1 we have write 4 inches in here. So same way which I have told you, you have to write the sizes from riser 1 to riser 2. That means from riser 1 to riser 2 there's a main pipe in here, and size is 4 inches, you have to write 4 inches. And from, let's say we take another, like riser 12 to 14, how we get 3 inches. So this is 12 and this is 14. In between them we have horizontal pipe, the main pipe, and you see that the size is 3 inches. Hot water pipe size is 3 inches. So we have write 3 inches. So in the same way you have to write the pipe sizes here one by one for the hot water. And hot water piping BTUs, how you will get this one? So you have to use a table for this thing. So you go back here and you check the piping heat loss per linear feet for 140 degree Fahrenheit water supply temperature and 70 degree Fahrenheit room temperature. Here if you see that we have bare pipes and insulated pipes. So if you have a bare pipes without insulation, you have to use these values. If you have insulated pipe, you have to use this column values. Since our pipe is insulated, half-inch fiberglass insulation, so this one. So first I have 4-inch pipe size, so I have to write the heat loss value for 4-inch pipe size with insulation. You see that it's 46, so I have to write 46 value in here. So same way you have to write one by one. So let's say 2 inches. 2 inches is how much? 28. So we have BTUs per hour. So we have to write 28 in here. So once this is done, you have to go for the next column, that is length. Length is very simple. You just have to go to your AutoCAD plan and you have to measure the length from one point to another point. So as per the AutoCAD plan, you have to check the lengths and you have to write lengths here. So I already write the lengths here. So if you can see that lengths are already mentioned here, like 20, 10, 10, 10, 20, 20, 30, 20, 20. So according to that, I have write all the lengths in here. So you just have to check it from the AutoCAD and write in here one by one. Now the next column is hot water piping total BTUs loss per hour. How you will get this value? Now we know that the length of the pipes and we know that BTUs per hour per unit length. So you just need to multiply these two figures, then you will get the hot water piping total BTUs loss per hour. So one by one you have to just multiply these two, like hot water piping loss per hour per unit length into length, you will get the hot water BTUs per hour. So one by one you have to calculate for all of the piping. So next thing over here is the hot water recirculation. This is the main thing which we are focusing on, because this is the hot water recirculation system design. So if you see in here, hot water recirculation piping BTUs loss per hour, this you have to calculate in here. And how you will get this one? Since we don't know the recirculation pipe size, this is what our case that we want to calculate the sizes for the recirculation system, hot water recirculation system. So we don't know the sizes for hot water recirculation system. So there is an assumption as per IPC, International Plumbing Code, or ASPE, American Society of Plumbing Engineers. But we have to do, there's a standard that we can, if we don't know the sizes, we can take 2 by 3 of this value. Which heat loss we calculated here, we can take 2 by 3 of this value. 2 by 3 means 0.67. So you just need to multiply this value with 0.67 and you will get the hot water recirculation piping heat losses. So one by one you have to multiply with 0.67. So this is a standard value, as I told you, as per IPC. So you have to calculate one by one for the hot water recirculation piping heat losses. So next thing you have to calculate here is the GPM, that is gallons per minute, to overcome the heat losses based on 20 °F temperature difference. As we mentioned earlier that supply temperature from the heater is 140 °F. So based on our assumption of 20 °F temperature difference, that means hot water supply temperature is 140 and recirculation is 120. So based on 20 °F we have to calculate the GPM to overcome the heat losses. So how you will get this one? You just need to add these values, that is for the hot water piping plus hot water recirculation piping divided by 10,000. You will get the GPM. So how did I get this 10,000 value? So I will tell you also how I get this one 10,000. So as we know that 1 gallon of water weigh 8.3 lbs, you can check over the internet that 1 gallon of water weigh is 8.3 lbs, so pounds, and 1 BTU is equal to heat necessity to raise 1 °F and recirculation for 1 GPM. Since it is based on 20 °F, so we just need to multiply this 8.3 based on 20 °F, so you will get 166 BTUs per minute. So if you want to convert into hour instead of minute, you just need to multiply with 60 and you will get 9,960. That is almost equal to 10,000. So this is why I have divided this value with 10,000. So one by one you have to get these values over here in this column. For this one you just need to add hot water piping total BTUs plus recirculation piping BTUs divided by 10,000. You will get the GPM in here. for that particular section of the pipe. So that means main from riser 8 to 10. This is our riser 8 and this is 10, and this is the main in here, horizontal pipe. So the GPM over here is 0.13 GPM, which we have right in here. So this is done. After that we'll go for the risers. So if you see that riser 157, I write it combined because the length was same, that's why I write 157 together, and 2414 I write together because of the length. So I have write together all of these just because of the length. So if you go for riser 1, 5 and 7, so 1, 5 and 7, so you have to check their lengths from the AutoCAD plans and you have to write the lengths accordingly. So riser 1, if you see that which pipe do we have in riser 1, hot water piping. I'm talking about the hot water piping, what we have here in riser 1 for the hot water piping. So if you see that in the riser 1 we have 2.5 inches, 2.5 inches, 2 inches, 1.5 inches and 1/4. So we have to write all this pipe there. You can see that 2.5, 2, 1.5 and 1/4. So all of pipe you have to write in here accordingly. And again you have to get this hot water piping BTUs per hour per unit length from the table. So 2.5 inch pipe, how much it is? 32. So 1/4, how much it is? 21. That is 21. So this is how you have to write one by one for each pipe size. So length, again I am telling you, you have to check from the AutoCAD plan and you have to write it. So I already write the lengths in here. So 160 feet, 27 feet, 18 feet and 6 feet. And for what you have to do, again you have to multiply in order to get your hot water piping total BTU loss per hour. You just need to multiply the length with per unit length BTUs loss. So you will get the total piping loss in BTUs per hour. So same way you have to do for this one and this one. So once you are done with this, you have to just get the total of this value, total heat loss for the hot water piping. And this one is again same assumption, we have to take 2/3 of this value because we don't know the pipe size for recirculation system. So we are going to take 2/3 value of this one. So if you multiply this with 0.67, that is 2/3 of this value. It is 4323 BTUs per hour for recirculation piping heat losses. And this thing again you have to calculate sum these two values and divide by 10,000. You will get the GPM, 1.08 GPM. So as you know that this is for one riser which we have calculated, and here if you see that we have 3 risers, that is 1, 5 and 7. So if we have 3 risers, that means you need to multiply this value with 3 and this value with 3. So I already multiplied this with 3 and this with 3. So we got the total BTUs for hot water piping and hot water recirculation piping heat losses for 3 risers. This is for individual riser and this is for 3 risers. So same way you have to other risers 2, 4 and 14. So I'm gonna take one more here just to save the time. I'm not gonna do for all of these. So I'm gonna take one more example here for riser 6. So if you see riser 6, so we will check now, check the pipe sizes in riser 6. So this is riser 6, and if we check the pipe sizes, this is 1.5. This is the hot water pipe sizing again. This is 1.5, this is 1/4, 1/4 and 1 inch. So we have 1.5, 1/4 and 1 inch, 3 pipe sizes here. So 1.5, 1/4 and 1 inches. That's how we write the pipe sizes in the riser, and we will write the heat loss values for each. Same way you have to check these values from this table and you have to write in here. And these lengths you have to get from AutoCAD plans and you have to write in here. And hot water piping BTUs per hour, you have to get, just multiply this per unit BTUs per hour loss for hot water with this length. You will get the total hot water heat loss per hour for the hot water piping. So one by one you have to calculate for all pipe sizes, and then you have to sum it up in here. And then what you have to do in here is you just have to calculate the second one, that is 2 by 3 of the total value, 2 by 3 of the total value. So you just need to multiply this with 2 by 3, that is we are taking 2/3 of this value, that is 0.67, and you will get the heat loss for the recirculation piping, hot water recirculation piping. So in the same way you have to get the GPM. You just need to sum up hot water piping BTUs per hour loss and recirculation hot water piping and divide by 10,000. You will get the GPM, that is 0.80. So this is how you have to calculate the BTUs and GPM for the remaining risers. So here we have 4 risers, you can see that. So you need to multiply with the 4 to get the total BTUs, and you need to multiply with 4 to get the total heat loss for recirculation and hot water piping. So after that what you have to do is you have to sum up your heat losses for hot water piping and recirculation hot water piping. So if you sum up the hot water piping heat losses, it's around 95,534 BTUs per hour, and if you check for recirculation losses, this one is around 64,000 BTUs per hour. Hot water recirculation piping loss 64,000. So total recirculation rate will be how much? It will be the sum of both hot water piping plus hot water recirculation piping. That is 1,59,542. That means almost 1,60,000 or 160,000 BTUs per hour. So how you will get the required flow rate? Required flow rate, how you will get? You just need to, same way, you just need to divide the sum of these two, that is hot water piping heat loss plus hot water recirculation piping heat loss, divide by 10,000 to get the required flow rate. So required flow rate for our system is, required recirculation flow rate is 15.95 GPM. So 15.95 GPM is required. And if you check in here, the next thing is uniform friction head loss. It is recommended to have a uniform friction head loss of 2 to 4 feet per 100 feet. So here we have taken 3 feet per 100 feet uniform friction head loss, and developed length of the run which we have to calculate, that means from heater to the most remote riser. So this is our heater and most remote riser. If you see that this is our most remote riser, that is 11 at story or floor number 11, floor number 24 we have the most remote riser, that is 11. So from here recirculation piping, if you check that hot water recirculation piping to the heater, this is our developed length total to the most remote riser, that is 11 number riser. So if you check from the AutoCAD plan, you can get these lengths, and according to that you have to write your lengths. So this is for the riser, due to the riser 207, this is from the riser recirculation 207, and this is for the horizontal piping to the main, from main to the heater. So 207 is due to the riser and 275 is the main piping length. So total is 482 feet is the developed length. So how we'll get the equivalent length of run? Since we don't know the sizes for recirculation, so we're gonna apply the general thumb rule for fittings to get the total equivalent length of run. So we know that the total piping length for the straight piece of pipe, but we don't know for the fittings and the valve. So what we're gonna do is we're gonna take 10% of this value to get the equivalent length of run. So you can see that this value plus 10% of this value, so we'll get 530 feet is the total equivalent length of run. So now we know that equivalent length of run, and we know the friction head loss, that is 3 feet per 100 feet. It is recommended value 3 feet per 100 feet, that's why we have used this one. If you increase this value to 5, 8 or 10, you will have more losses. That's why we have selected 3 to have a uniform losses. So if you want to calculate the head required now for recirculation system, so how you will get that? You just need to multiply this uniform head loss with the equivalent length which we have calculated in here divided by 100. You will get the head. So head for recirculation system required is 15.91 feet. That means 16 feet head is required for the recirculation system. And GPM we already calculated, that is 16 GPM. So now the last thing which we have to do here is we have to size the hot water recirculation system. This is very important. So how we did this thing? So basically I have used this formula. For the brass or the copper piping you have to use this equation, and for galvanized or steel pipe you have to use this equation. Since we have a brass or piping, so we have used this formula. So we have the H value, head we know that 16, and length, its per unit length we have calculated here. So if you, and Q we also know that is 16 GPM in here. So if you know all the values in here, so the thing which remaining is D, that is diameter for piping. So you can calculate easily after putting all the values. So based on this thing, there is a formula developed in here. If you change the GPM one by one, you will develop this this thing, that is half inch is equal to 1.8 GPM. So from this equation I got this values: half inch equal to 1.8 GPM, 2 inch equal to 34.6 GPM, and 4 inch equal to 181 GPM. So now we are going to use one by one to calculate the recirculation pipe sizes. So one more thing, if you have to check in here, for all the risers, if you see that GPM is 1.08 for 157, and 2, 4 and 14 GPM is 1.02, and 1.14, 1.80, 1.04, 0.92. So you can see that minimum GPM here is 1.8 GPM, and all the GPM which we have calculated in here for the risers are less than 1.8 GPM. So the minimum size, if you see that here is half inches available, that means our riser will be half inches, all the risers, because their GPM is less than 1.8. so we can use half inch in here, but we will not gonna use half inch. The minimum size recommended is 3 by 4 inches. So instead of half inches, we're gonna use risers 3 by 4 inches. The reason why I'm gonna use 3 by 4 inches instead of half inches, because pipe size will be very small, and with the time maybe deposits will be developed inside the pipe and it will gonna clog the pipe. So it is better to use 3 by 4 inches pipe size instead of half inches, even if it is 1.8 GPM. So I'm gonna use minimum pipe size is 3 by 4 inches for all the risers. If you see that all GPMs is less than 3.5, so all the riser size for the recirculation hot water, it will be for risers, it will be 3 by 4 inches. So riser size is done, 3 by 4 inches. Now what we're gonna do, we're gonna calculate the size for the main recirculation piping in here, like between 9 to 11 riser, between 6 to 9 riser, between 5 to 7, between 1 to 2. We have to calculate the main horizontal piping. So we'll do one by one. So first is riser 11. So we'll start from the most remote one. If you see that this is riser 11 in here, and we're gonna get the size for this main recirculation pipe in here, which is connected to water heater in here. So we'll go one by one and calculate one by one size to the water heater recirculation pipe sizes. So here you have section 11. This is riser 11, and we are going to get the size for this horizontal pipe in here, this one. So this is we have 11. If you see here, this is riser 11 plus main 9 to 11. First we calculate the GPM, and based on GPM we will get the sizes. So between 9 to 11, if you see that how much is the GPM we got from main, from riser 9 to 11, this one. If you see the GPM is 0.12 between 9 to 11, between 9 and 11 riser, and 11 riser is how much GPM? Riser 11, this one, remember that 0.12, and riser 11 is 0.92. So 0.92 and 0.12. So 0.92 plus 0.12 is 1.09 GPM total. So if you see that 1.09 GPM based on the assumption and based on the values applied to this formula, we got this thing. So 1.09 so 1.09 is less than 3.5 GPM. So we can use 3 by 4 inch pipe size in here. So we're gonna use 3 by 4 inch pipe size for this one. So that means we can use 3 by 4 inch pipe size up till 3.5 GPM. If we have 3.6 GPM, then we have to increase the pipe size to 1 inches. So I'm gonna take another example in here. So let's take second one also, 1.04. So 0.92 plus 0.12, it is 1.04, sorry. So let's take the second main pipe size. So now we will calculate the size for the second one here, second one. So if you see the second one is riser is 9. We have to add this value also, which we calculated earlier. This value, first value which we have calculated here, plus riser 9 GPM value, plus between sections riser 6 and 9. So if you check previous value which we'll add, that is 1.04, which we have right in here, plus riser 9 plus main 6 to 9. So if you see that riser 9 GPM is how much? You see here that is 0.92. So we have to write riser 9 0.92, and the last one here is main 6 to 9. If you check the main from 6 to 9, this one GPM is how much between 6 to 9? So main from riser 6 to 9 GPM is 0.11. So you have to write 0.11 here. So you know all the GPMs now, just add it, total it will be 2.07. Again 2.07 is less than 3.5 GPM, so we can use 3 by 4 inch pipe size. So we have used 3 by 4 inch here. So I'm gonna use some other example here now. So let's say I'm going to calculate for this one. So you have to consider the previous one also. Previous one is 11.34 plus riser 3 and main 4 to 3. That is main is this one, riser 3 and main 4 to 3. So if you see that riser 3 is in here and 4 is here, so we have to check GPM for this riser 3 and all the GPM, previous GPMs here, plus riser 3 GPM to get the size for this pipe segment. So what you have to do is GPM for riser 3 and GPM for between riser 3 and 4 and the previous all GPMs. So riser 3 is how much? 1.14, and between 4 to 3 is 1.08. So you can see that riser 3 value is 1.14 and 0.08 is for main between 4 and 3, and this is the previous GPM which we have to add in here to get the size for the next pipe segment. So if you see that total which we calculated here is 12.56 GPM. So 12.56 GPM, if you see here, it's 12.4 GPM. Up till 12.4 GPM you can use 1/4 inch, but since this 12.56 is greater, so we have to increase the size to 1.5 inches. So that's why we have used 1.5 inch for this pipe segment. So you can use 1.5 inches up till 18.3 GPM. You can use this size. After that you have to increase the size again. So one more last item I will tell you here. Same way you have to do for this one also. So last item is riser 1 plus main 2 heater. So if you see here, so last item we have riser 1 and all the previous GPM which we have calculated to get the size for this pipe segment. To get the size of this pipe segment, you have to add all the GPM which you have calculated in here plus riser 1 GPM, and this main pipe GPM, recirculation main pipe GPM. So from section 1 to the heater. So if you see that from heater to the riser 1, how much is the GPM? We calculated 0.15, and the riser 1 GPM, how much we got in here? That is 1.08. So 0.15 and 1.08. So if you see here, 1.08 for riser 1 and 0.15 is for main to the heater 1, and 14.6 is the previous GPM which we have calculated. So adding all these values, you will get 15.99 GPM total. So 15.99 GPM is less than 18.3 and greater than 12.4. So that means we can use 1.5 inch pipe size in here for that pipe segment. So this is how you can do the hot water recirculation pipe sizing, or you can design your hot water recirculation system. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe. Thank you. Hello guys, this is Saeed Mohammad Waqas. The topic which I am going to discuss today is related to the combined stormwater and sanitary system design. As you can see that there I have prepared an Excel sheet for this combined stormwater and sanitary systems design. So this is the drawing which I'm gonna use, and I will calculate the pipe size of each segment represented here on the drawing. So these are the tables which I'm gonna use during calculation. So first of all, you can see here we have a pipe mark. You can see that I have divided each pipe segment and give it a name. So here it is represented by pipe mark, and then we have a fixture unit, then we have a demand, and then equivalent drain area in a square feet. Since this is a combined stormwater and sanitary system, we need to convert this fixture unit represented here on the drawing, because this fixture unit is from the sanitary drainage system. We need to convert this into equivalent drained area and write it here in this column, equivalent drained area. So for stormwater, is you can see that we directly here we have a roof area in here that is going to be drained is 4,000 square feet, and here it is represented 3,500 square feet, but we need to convert these fixture units into the equivalent drain area, and we can write in here. And then you can see the pipe breakdown. That means if you see in here this pipe section C, since the flow is from point A, flow is towards the point C, so flow at point A and point B. So flow at point C, it will be the sum of point A and B. So we're gonna calculate up till point Q, and we'll do the sizing up till point Q. So we're gonna start from this furthest outlet 256 fixture unit, stack P2 point. So first thing over here, important thing is here the location. So where are you going to perform this one? Because rainfall rate is different for each city in the country, or different in different countries. So first of all, we have to check the location. Since I'm talking about New Delhi, India, so first I have to get the maximum rainfall rate in inches per hour in New Delhi. So there I have table here for 72 different cities in India. So since you can see that rainfall per hour, this is for 1 hour, this is for 3 hours, this is for 6, and this is for 24 hours. Since I'm talking about New Delhi, per hour rainfall rate in centimeter is given here. So as you can see here, its rainfall is per hour is 11.17 centimeter per hour. So if I want to convert this into inches, how much it will be? 11.17 divided by 2.54, that means 4.39 or 4.4 inches per hour. So that's how I write here 4.4 inches per hour for New Delhi. So for different cities, almost 72 cities data is in there, you can choose the cities. So here the procedure for combined stormwater and sanitary drainage system, there's a procedure that which we need to follow as per standard. that if you have less than or equal to 256 fixture units, then equivalent drained area you take is 1000 square feet. Let's say if you have 200 fixture units, then equivalent drained area which you will take as per procedure is 1000 square feet. And if you have more than 256 fixture units, then equivalent drained area, how you will get the equivalent drained area, 3.51 square feet per fixture unit. That means every increment in the fixture unit after 256, you need 3.51 square feet per fixture unit. And how did you get this value, I will tell you later. So this is the piping slope which we have used in our project, that is 1 by 1/8 inch per foot slope which we have used in here. And now I will tell you how did I get this 3.51 square feet per fixture unit. If you have more than 256 fixture units, for every increment in the fixture unit after 256, you have to use 3.51 square feet per fixture unit. This depends on the rainfall. So since we know that 1 GPM is equal to 60 gallons per hour, so if you want to convert this gallons per hour to cubic feet per hour, you need to divide 60 divided by 7.5. You will get 1 GPM is equal to 8 cubic feet per hour. And we know the rainfall rate in New Delhi is 4.4 inches per hour. If you want to convert this inches to feet, so simply you need to divide 4.4 divided by 12, you will get in a feet, that is 0.37 feet per hour. So now we want to get the how much GPM will be conveyed from the surface, because here if you see that we have a GPM also, so how much GPM will be conveyed from the surface should be converted to equivalent drained area. So that's why we are converting this one. So how you will get this 21.82 square feet, you just need to divide this 8 cubic feet per hour by 0.37 rainfall rate in New Delhi, India. So you will get 21.82 square feet. Now what does it mean, 21.82 square feet? That means 21.82 square feet of horizontal area is equivalent to 1 GPM that must be conveyed from the surface. Or in other words, the 1 GPM collect on 21.82 square feet of horizontal surface if you have a rainfall rate of 4.4 inches per hour. So now we'll go towards the pipe sizing of this combined stormwater and sanitary system. Before proceeding towards sizing, there's one announcement that if you guys join the channel membership, you will get access to exclusive perks like Excel sheets, softwares, and drawings. Whatever I use in the video or in the future videos, you will get access if you have a membership on the channel. And this channel membership is really cheap, around $2 per month. So if you guys want to join the membership link is given in the description, you can join from there. So before proceeding towards the pipe sizing of the combined storm and sanitary system, you can see that this is a combined system we have in here. This is a sanitary drainage piping line, and this is the stormwater line, and here it's combined together, and same thing over here. And one thing you need to understand about the leader pipe and the sanitary drainage pipe. So let's me go to the piping section and explain you here. So as you can see here, this is the combined stormwater and sanitary drainage system. This is the soil stack pipe, and this is the runout from the stack, and this is the main combined storm, this main combined storm and drainage pipe. And you can see that this is the leader pipe for the storm water, and there we have a trap, and then we have horizontal pipe in here. It is important to understand this thing before proceeding towards the pipe sizing. So you can see that the stormwater connection should be at least 10 feet downstream from any branch of the building drain. As per the code, you have to maintain minimum 10 feet distance between the soil stack and the stormwater pipe. So now proceed towards the sizing of the system. And one more thing you can see in here, that this is the roof over here, and this is a roof drain through which water will be drained down. And this is basically a primary scupper, and here you can also see that we have secondary scuppers. These are the secondary scuppers installed in the parapet wall. These are the parapet walls. In case this drain is blocked or clogged, in that case water will drain down from the secondary scuppers, as you can see in here. And these scuppers are installed normally 2 inches above the roof level. So first we'll start from this point, and we'll go up till point Q. So we're gonna start from this point. You can see that this is the stack P2 over here. This is the stack we're talking about. This is the stack pipe, and this is a horizontal run out from the stack. So there we have a stack with 256 fixture unit represented by P2. So pipe P2, 256 fixture units. Since we said in here that 256 fixture units, if we have less than 256 fixture units, then equivalent drained area we get is 1000 square feet as per code. So 1000 square feet we have to use in here. But before that, I forgot to tell you how did you get this 3.51 square feet per fixture unit. So since we know that 1 GPM conveyed to 21.82 square feet of the horizontal surface if you have a rainfall of 4.4 inches per hour. So this 0.161 you need to multiply with this area which we got here is 21.82. And how did we get 0.161? So every fixture unit after 256 required 0.161 GPM. So that's why we write 0.161 into we talk about 1 GPM is 21.82. Once you multiply these two, you will get 3.51 square feet per fixture unit, and this will be used only if you have fixture units more than 256. Then each fixture unit drainage area you will get by 3.51 square feet per fixture unit. If you have less than 256, less than or equal to 256 fixture unit, then you will get by this procedure you have to get 1000 square feet drained area. Since we have 256 fixture unit in here, so we are going to use this 1000 square feet area. You can see that equivalent drained area is 1000 square feet. So now the reference table here which we have to use is 6-3 to get the pipe size. Since this is a stack pipe and we have more than 3-story building, so this is the 6-3 table. There you see 3 columns in here. If you have seen my drainage pipe sizing video or drainage system design, I have used the same table 6-3 and 6-5 for drainage system sizing for the stacks and the runouts. If you have not seen that video, I will give the link in the description below. You can watch it. So since we have more than 3-story building in height, so we have to use this column in here. So how many fixture unit we said? 256 fixture unit in here. So 256 fixture units. 256 fixture units is this is 60 and this is 500. So 250 in between them, so we'll go for the higher value 500, and if you will check here is 4 inches. So that's how we got 4 inches pipe size in here. Then move to the section A. Section A is basically the run out from the stack. This is basically a run out from the stack, so we have to use table 6-5 to get the pipe size. We know the fixture unit at point A is also 256, it's same. So this is the run out, so we're going to use table 6-5. So this is table 6-5 which I'm gonna use. Since we know that the slope which we have used here is 118 inches per foot, and fixture unit is how, so we have to follow this column 18 inch per foot slope. 256 fixture units in between them, so we'll go for the higher value 390. You check the pipe size here is 5 inches. So the pipe size from the stack to the run out to the main pipe is so this section A is 5 inches, this using table 6-5. So now we'll go to this is stormwater pipe having a drained area of 3500 square feet. Surface drained area is 3500 square feet, and then we have a trap in here, as I talked here about the trap. This is a leader pipe, this is a trap, and this is a horizontal pipe. So first we'll talk about the leader L2 before trap. This is the leader L2 having 3500 square feet. You can see in here. So we have to use table 7-1 to get the size for this L2. So I'm gonna use 7-1 table, and since we are talking about the leader drained area, so we're gonna use this column, and we said that 3500 square feet. So 3500 square feet is in between 2200 and 4600 square feet, the leader drained area column. So we'll go for the higher value, 4600. So if you check, the pipe size in here is 4 inches diameter, so we have to use 4-inch here. So after the trap, you see the horizontal pipe here. This is represented by B. This is represented by B. So 3500 same equivalent drained area at this point. So we have to get the size from the same table 7-1. But this time we have to use 1/8 inch per foot slope column, because this is the horizontal piping drained area for the various slope. Since we know our piping slope is 1/8 inch per foot, and 3500 is in between these two, 3340 and 5350. So we'll go for the higher value, that is 5350. Then this is basically a fixture units. So if you see over here to the left side, the pipe diameter is 6 inches. So that's how we got 6 inches pipe size in here for section B. Now if you see the section C, it is the sum of the flow from the point A and the B. That's why I have written here is C equal to A plus B. Now if you check the drained area at point A is 1000 square feet. We already converted 256 fixture unit to 1000 square feet, and this one is already in square feet, equivalent drained area in square feet. So total it will be 4500 square feet at point C. How we get this 256 fixture unit equal to 1000 square feet, we already talked in here. So total now here is 4500 fixture unit. It is a combined system for stormwater and sanitary system. So we're going to use 7-1 table to do the pipe sizing for at point C or section C. So C section 4500 square feet, use table 7-1 again. So 4500 square feet is in between these two values, so we're gonna use the higher value 5350 fixture unit and check the pipe size in here. Again, this is horizontal piping, so we are using 1/8 inch per foot slope. So 5350, the pipe diameter is 6 inches, so we have used 6 inches in here. So in the same way you have to do for other pipes in here, like 180 fixture unit, 4000 square feet, and then at point F it will be the sum of D and E. And then how you will get for G, it will be the sum of C plus F. And then same way you have to do for this P4 stack, then horizontal run from the stack represented by H, and then P3 stack, and then horizontal run is represented by I, and then you have J over here, and then at point K it will be the sum of G plus J here, that is G plus J. And then you have to do for this one, and for this GPM you have to use since we talk about 1 GPM conveyed equal to 21.82 square feet, so equivalent drained area you just need to multiply 120 with 21.82, you will get the drained area for this one. So now I'm talking about this last one over here. So I will do the sizing for stack P5 first, having 400 fixture units. P5 400 fixture units. So this is the stack P5, so we're going to use the table 6-3. So more than 3 story we have to use again, and 400 fixture units in between 60 and 500, so we'll go for higher value 500, and we'll check the pipe size is 4 inches. So P5 is 4 inches. Again we have the horizontal run from the stack, that is represented by N. So for horizontal run out from the stack, we have to use table 6-5. You can see in here again same fixture units from the stack. So 6-5 maximum per visible fixture unit load for this one, you can see in here. The slope for the pipe is 1/8 and 400 fixture units. So we have 390 and 700. So we go for the higher value 700, that is more than 390 fixture unit, and you will check the pipe size here is 6 inches, having 1/8 inch per foot slope. So here you can see that 6-inch pipe size we have used in here. Now next is O, that is coming from the sump having 100 GPM drain from that point. So this is 100 GPM, we know that. So we are going to use 1 GPM required one fixture unit over here. So 1 GPM required one fixture unit in here. So 100 GPM required 100 fixture unit in here. So we have used 100 fixture unit. And again this is the runout from the sump number 2. So for the runouts we have to use this table having 1/8 inch per foot slope, and 100 fixture units between 20 and 180. So we'll go for the higher value 180, and pipe size is 4 inches. So we have used the pipe size 4 inches here. So next is point P. It will be the sum of point N plus O. P, that is the sum of N O, you can see in here. And if you see the fixture unit which we calculated here is 100, and at this point we have point N is 400, point O is 100, and is 400, you can see in here. So total fixture unit at point P, it will be 400 plus 100, that is 500 fixture unit in here. So again this is the horizontal run out here for drainage system. There is no stormwater pipe in here, so we can use table 6-5 to do the sizing for section P. So 6-5, 1/8 inch slope per foot, we have to use this one, and we talk about 500 fixture units. So 390 we have, 700 we have. So we'll go for 700 and check the pipe size, because we don't have 500 in here. So we'll use 700. So 700 pipe size is 6 inches. So you can see in here for P section pipe size is 6 inches. Now the last section here is Q. Q, it will be the sum of the flow from point M and P. You can see in here M and P. So M, we know that if we already calculated in here, the equivalent drained area for M is 12397 square feet. And for point P, we have fixture units. We don't have the equivalent drained area, so we need to convert this fixture unit into equivalent drained area. So G47 is this value. We directly have the equivalent drained area plus this value. Fixture units are 500. Since we said that if we have fixture unit more than 256, so we require 3.51 square feet per fixture units. So we have 500. So 500 into 3.51, it will be 1755 plus 12397. 12397. Sorry, again. 500 into 3.51, plus 12397. So total here is 14,152 equivalent drained area. You can see in here this equivalent drained area at point Q is 14,153, 14,152 or 14,153 here, which we have calculated here because we have the equivalent drained area directly in here, but this fixture unit we need to convert this into equivalent drained area. So 500 fixture unit, we know that is 3.51 square feet. Since we have 500, so 500 into 3.51, total 1700 something plus this one. So total fixture unit is 14,153. Since we know the fixture units now, this equivalent drained area in a square feet, so now we can get the pipe size in inches using table 7-1. So again you have to use this is again the horizontal pipe. This one Q is again the horizontal pipe, so we have to use again this horizontal piping 1/8 inch per foot slope, and then you have to check 14,153 fixture units, and 14,153 fixture units you have to check in here, and you will get the pipe size that is 10 inches. So this is how you can do the combined stormwater sanitary drainage system sizing. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe and don't forget to press the bell icon. Thank you. Hi guys, it's Syed Mohammad Wakas. The topic which I'm going to discuss today is related to chilled drinking water system design calculation, and this is the spreadsheet which I'm going to use for this designing of chilled drinking water system. So let's get started. Before starting the design calculation, let me just tell you about the spreadsheet. I have used the different colors just to differentiate. So this basically green color are the input values from the user. Green text is basically the input values from the user, and the red color values depending on the type, depending on the selection which you made from the top 4 rows. So as you can see here, green and the red color. So first of all, you have to determine the type of the building in which you are going to place this chilled drinking water system. So you have to select from here the type of the building. So based on the type of the building, if you select the restaurant, you can see the gallons per person is 0.1 gallon per person. So this value will be changed based on the type of the building. So if I select the hospital, this value will be changed. So let's say I'm going to perform the calculation for school building. So if I change this to school, you can see that gallons per outlet per hour is 5 gallons. Now the second thing over here is the water inlet temperature. So you have to check this water inlet temperature from the local authorities of your area. So let's say I'm going to use 75 degrees Fahrenheit of water inlet temperature. If I change this to 75 degrees Fahrenheit, you can see that this value will be changed. The BTUs per hour per gallon will be changed. So this value BTUs per hour per gallon depend on your water inlet temperature. So if I change this to 90, this value will be changed to 374 BTUs per gallon. So here I'm going to use water inlet temperature at my area is 75 degrees Fahrenheit. So I'm going to use 75 degrees Fahrenheit. And this design of drinking chilled water, it's on 45 degrees Fahrenheit supply temperature. So we are going to supply 45 degrees Fahrenheit supply temperature at the drinking fountain, and the water inlet temperature is 75 degrees Fahrenheit. And next thing come over here is the room temperature. Room temperature where we are going to place the fountains. So drinking fountain area temperature which I have selected here is there are total 3 temperatures 70, 80 and 90 degrees Fahrenheit. So normally we are placing at the corridors area, so I'm going to use 80 degrees Fahrenheit is the room temperature here. So this 80 degrees Fahrenheit if you select here, so these values comes up. If I change this to 70, from here room temperature. If I change this to 70, then these values will be changed accordingly. These circulation losses in the pipes as well as for the circulation pump capacity calculation. Later I will tell you about this. So I'm going to select 80 degrees Fahrenheit here. So next thing over here is the pump horsepower. So how in this we have to assume over here, it's if you see here we have pumps from 1/4 to 2 horsepower. So we are going to assume the pump horsepower of 3/4. So based on this selection, your heat load will be calculated for your pump. So if I use 3/4, you can see that this circulation pump heat will come here, which is 1908 BTUs per hour. If I change this to, let's say, 2 horsepower, then this value will be changed to 5090. So circulation pump heat input depends on the horsepower of the pump which you assumed in here. So here I'm going to assume the horsepower of 3/4. So next thing, you have to count the number of outlet. As I told you, green color is the input from the user. So you have to go to the drawing, count the number of outlets and use in here. Let's say the number of outlets check from the drawing is 60, and these values, as I told you, depending on the selection which you made here. So now we have to calculate the load due to the above usage here. So simply multiply these three values and you will get the load, that is 75,000 BTUs per hour. So next we have to calculate the losses, circulation losses in the pipes, this one. But before that we have to write all the piping lengths which we have used in our project. So you have to write all the pipes in here, whatever you have used in your project. Then you have to go to the drawing and write the length in here. You have to check the length of each pipe segment and add it in here. So after checking the lengths in the drawing of each pipe segment, I have write in here, let's say these are the lengths which I have right here, and we need to convert this into feet. So I just need to multiply this value with 3.28 to get this length in feet. So you have to write in here everything, and then you have to proceed towards the circulation losses in the pipes. So now I have to calculate the circulation losses in the pipe. So I have write the pipe lengths in here, which is the same as here, and these values in BTUs per hour per 100 foot of the pipe. So these values depending on the room temperature which you selected in here, 80 degrees Fahrenheit. If I change this to 90, the values will be changed, these values will be changed accordingly. So I have selected 80, so these values are in here. So simply you need to multiply length with this one. You will get the circulation losses in the pipe in BTUs per hour. Since this value is in per 100 foot of the pipe, so you need to multiply them and divide by 100 to get in BTUs per hour per foot of the pipe. So total losses you calculate here is 4,650 BTUs per hour. So now the third thing which we have to calculate here is the circulation pump heat input. So as I told you, it depends on the horsepower which you assumed in here. So 3/4 horsepower which we assumed here, the circulation pump heat input is 1908 BTUs per hour. So now we have to add all of these load which we calculated, that is 75,000, 4,650 and 1908. After adding all these values, we get the total BTUs per hour, 81,558 BTUs per hour. Now we are going to use 15% as safety factor. So 15% of this will be added into 81,558. So total BTUs per hour calculated here is 93,792 BTUs per hour. So load is done. Now we proceed towards the circulation pump calculation. So in circulation pump calculation, we will calculate the circulation pump capacity. in GPM, as well as we'll calculate the circulation pump head. So I have all the pipes which I have used in this project, and again these are the lengths, the same which I computed here above, and these values in the red color are again the same depending on the room temperature which you selected in here, 80 degrees Fahrenheit. So these values in gallons per hour per 100 foot of the pipe. So again you need to multiply this 600 with 14.6 and you need to divide by 100 because this value is in per 100 foot of the pipe. So we'll get the value of 88 gallons per hour for 1 inch pipe. So same way you have to write for 1/4 and 1.5 inch pipe, and you get the total gallons per hour, that is the sum of all of the above. So it is 135 gallons per hour. So again we have to add 20% as a safety factor. So after adding 20% safety factor, we will get total 162 gallons per hour. So if I want to convert into GPM, divide by 60, divide this value by 60, I will get 2.7 GPM. But this is not it is not decided that we are going to use 2.7 GPM for the circulation pump. We need to check one more thing and then we decide we are going to use or not. So minimum we use 3 GPM per circuit in designing of the drinking chill water system. So number of circuits we have to check. So we have to go to the drawing and check number of circuits. So let's say we are going to use 5 circuits and we say that minimum 3 GPM is required for each circuit. So total value which we calculate here for circulation pump is 3 into 5, which is 15 GPM. Now we have to decide, so whichever value is greater here, so we have to use as circulation pump capacity. Now this one we calculated is 2.7 GPM, and this value which we calculated here is 15 GPM. 15 is greater, so we're going to use 15 GPM is the circulation pump capacity. So you have to decide based on which our value is greater. So I'm going to use circulation pump capacity of 15 GPM. So now I'm going to calculate the circulation pump head. As you know that for the head calculation we have to check the furthest pipe length for supply and return. And to calculate the head we have total 2 type of losses which we have to compute. One is the straight pipe length loss and fittings and component losses. So here I am going to assume 50% of straight pipe length losses to be used for fittings and components. So that's why I multiply this with 1.5 here to get the pump head. So we need to multiply uniform friction head loss with 1.5 to get the circulation pump head. As I told you in the previous videos as well, uniform friction loss we normally use is 4 to 6 per 100 foot of the pipe. So here I am going to use 4 foot per 100 foot of the pipe as the uniform friction loss. So 1.5 into, you need to multiply this with the total piping length. So we have uniform friction head loss. As I told you, I have used 4 foot per 100 foot, so 4 divided by 100 into total piping length. So again you have to go to the drawing and you have to check the furthest piping length. That means from the source of supply, which in that case is circulation pump. So from circulation pump to the furthest outlet in the drinking chill water system, you have to check the length. Let's say it's 100 meter, which is equal to 328 foot. So you have to use this value in here. So circulation pump head will be 1.5 into 4 divided by 100 into 328. So head calculated here is 19.7 feet. If you want to convert this into psi, just multiply this with 0.433. you will get the head loss of circulation pump in psi. Now the one last thing you have to calculate here is the gallons to be cooled. That means storage capacity we have to calculate here now. So in order to calculate the storage capacity, first thing I have to do here, I have to use this formula. BTU is equal to gallons to be cooled into delta T into 8.3. So this formula I'm going to use in here. So gallons to be cooled, I know that the BTUs, total BTUs I have calculated here is 93,792, which I have written here. So gallons to be cooled is equal to this value divided by delta T into 8.3. Now delta T, as I told you, the water inlet temperature is 75 degrees Fahrenheit here, and the supply and the chilled drinking water system temperature which we selected here is 45 degrees Fahrenheit. So 75 minus 45 equal to 30. So we have to write 30 in here. 75 equal minus 45 equal to 30. So gallons to be cooled calculated here is 377 gallons. Now we assume that 50% of the water will return back to the chiller and 50% will be consumed. So that 50% will come from the makeup water. So now we are going to calculate the storage capacity. So if we calculate the storage capacity, since we said that 50% of the water will return back to chiller and 50% will come from the makeup water, so we just need to multiply this gallons to be cooled with 0.5 to get the storage capacity. So now we got all the values. As you can see here, chiller cooling load which we calculated is 93,792 BTUs per hour, this one, and storage capacity which we calculated here is 188 gallons based on 50% of the water returned back to the chiller. And number of pumps we are going to use here is 2, one duty and one standby. And circulation pump capacity which we calculate here is 15 GPM based on the assumption of 3 GPM per circuit. And circulation pump head which we calculated here is 8.52 psi. So this is how you can do the calculation for chilled drinking water system. I hope you guys learned something from this video. For more videos, keep watching my channel. Don't forget to subscribe. Thank you. Hello guys, this is Syed Muhammad Waqas. I am back with another video. In this video, I will tell you guys about water supply pipe sizing, cold water and hot water, both of them pipe sizing. So here you can see that I have a drawing for two-story factory building equipped with 2 toilet rooms. As you can see over here, first one toilet room and the second toilet room, and the highest fixture you can see from this is the street main over here. So highest fixture is located over here. This is the 8 feet and this is 13 feet. So total height is from street main to highest fixture is 21 feet. So highest fixture is located 21 feet above street main. And over here in the street main we have a 2-inch corporation caulk at street main, 2-inch corporation caulk, and pressure loss through that caulk we can get it from supplier. And minimum pressure available at street, this is the street main, and the minimum pressure available at street main is 55 psi. So this value you can get from local water authorities on your location. And let's move to this tab. So this is the table we are going to use to calculate hot and cold water pipe sizing. As you can see over here, the things which I already mentioned before, like minimum pressure available at street main is 55 psi. This value you can get from the local water authorities on your area. So highest pressure at the fixture is 15 psi. As you can see that this is the highest fixture we have over here, and as explained that the highest fixture group consists of flush valves So basically you need to understand two things first. If you have a highest group of fixture contain flush valves, then the pressure for that group should not be less than 15 psi. This is as per International Plumbing Code IPC. And if your highest group of fixture contain flush tanks, then the pressure for that group should not be less than 8 psi. Since we have flush valve over here, so that's why we took 15 psi as per International Plumbing Code IPC. So that's why we have 15 psi is the pressure loss for this highest pressure required at the fixture. And we have a 2-inch water meter over here, 2-inch water meter. As you can see in the drawing, there we have a water meter over here. It's 2-inch, and the pressure loss to that meter you can get that from supplier. As you can see that the pressure loss we got from supplier manufacturer is 1.61, and the static head loss is 21 feet. Static head loss is due to the change in elevation. As you can see that from the street main to the highest fixture we have total height is 8 feet and 21 feet. So elevation difference is 21 feet from street main to the highest fixture. So we got the static head loss is 21 feet. Since we know that 1 is equal to 0.43 psi per feet, so in order to convert this into psi you need to multiply this with 0.43 psi per feet. So after multiplying this 21 into 0.43 you will get 9.03 psi static head loss. And then we have a special fixture loss like backflow preventer. Since you can see that in the drawing we have a one backflow preventer over here, and this is 3-inch backflow preventer. We need to get this value, pressure loss value or friction loss value from the supplier for the backflow preventer. So we get this value from the supplier, that is 9 psi. And if you have any other special fixture loss, like if you have filter or water softeners or anything, you need to mention over here these losses. So as you can see that we have mentioned each and every pressure loss with the different line A, B, C, D, E, F, G, H, I. So we need to add all these losses from point B to point H. So line B to line H, total losses 15, 11, 1.61, 9.039. So total friction loss is 45.64 psi. As you know that we get this minimum pressure at street main from local water authorities is 55 psi. So now we need to subtract this total pressure available at street main minus pressure losses through water meter, taps in the main, static head loss. We need to subtract all these losses. So this is the pressure available to overcome pipe friction, that is line A minus J. A is 55 and J is 45.64. So after subtracting you will get 9.36 psi. So 9.36 psi is the pressure available to overcome the pipe friction. So now as you can see that we need to divide our into different sections. We have divided the drawing into a different section where major changes in elevation or branches lead to the fixture group. So A to B, this is one section, B to C one section, C to D one section, and D to E one, and then C to F another section. As you can see that how many fixture units we have over here: 288 fixture unit here, then we have 264 fixture unit here, B to C, and then 132 fixture unit here, 132 here, 132 here, and B to C we have 24 fixture unit, and then C to F we have 12 fixture units. And the lengths are given: A to B 54, B to C 8 feet, C to D 13 feet, and D to E 150 feet. So everything is mentioned in the drawing. So let's move back to our table. As you can see that we have a fixture unit for A to B is 288, then B to C we have 264, C to D 132, and C to F 132, and D to E 132. So now we have to get the gallons per minute through each section, because while doing water supply pipe sizing, we have to do it using a fixture unit, water supply fixture unit method. So load values of fixtures must be determined as water supply fixture unit. Then we need to convert them into gallons per minute to determine the peak demand. So we need to convert these fixture units into gallons per minute. So 288 fixture unit, then 264. So let's move to tables and charts over here, and we are going to use this table, this one 103.3. as you can see that this is the load, this is the demand, and this is for flush tanks, and this is the load demand for flush valve. Since we are using the flush valves, so we need to use this columns. So we have 288 fixture water supply fixture units. Since we have 275 here and 300 here, so we are going for the higher value for the safety. So 300 fixture unit, the demand will be 108 GPM. So move back there, 288 108 GPM. Then 264, how many GPM? 264 fixture unit, this is 250 and this is 275. So we don't have 264, we will go for the higher value, that is 275. 275 load, we will get 104.5 GPM load. So 104.5 GPM. So same way you have to check for 132 for each, you will get 77 GPM for each. So now we need to check the length of each section, A to B, B to C, C to D, D to E, and C to F. A to B is 54. As you can see, A to B is 54, B to C is 8, C to D is 13, and D to E is 150, and C to F is 150. So you can see that all the lengths we have mentioned here, 54, 8, 13, 150 and 150. So now the third thing is, in this column, column number 5, we have to check the trial pipe size. So the trial pipe size, how to get the trial pipe size? Trial pipe size, there is a formula which we have to use to get the trial pipe size. This is the formula, that is pressure available to overcome pipe friction divided by equivalent length of run to the most remote outlet multiplied by 100. So if we move back to our drawing, you can see that the most remote outlet is here. So total length from street main to the most remote outlet is how much? 54 feet, 8 feet, 13 feet and 150 feet. If you add all of them, how much length you will get? That is 54 plus 8 plus 13 plus 150. So total you will get 225 equivalent length of the straight piping. So we did not add any length for the fittings and the valves. So as a rule of thumb, we can add now 50% of the straight length of the pipe, just for now, as a trial pipe, for the trial pipe size. So 50% will be 112.5 plus 225 equal to 338. So total equivalent length of run is 338 feet. So now we know that the pressure available to overcome pipe friction, that is 9.36, we already calculated. We know that equivalent length of run to the most remote outlet, that is 338 feet, we just calculated now, multiply by 100. So pressure available to overcome pipe friction, as you know that we calculated here, that is 9.36, this value. So 9.36 divided by 338, total equivalent length, multiply by 100. So how much friction loss we get? That is 2.77 psi per 100 feet. This is the average friction loss, that is 2.77 psi per 100 feet. So based on this 2.77 psi per feet, it's the average friction loss, and demand and the GPM we already know that this is 108. So 108 GPM is the demand, and we know that average friction loss is 2.77 psi per 100 feet. So now we are going to use one chart. And one more thing, all the piping which we used over here is copper L type piping. So when we go over here, this is the chart for copper K type. Since we use this copper L type in our project, so we need to use this chart, that is 103.3 figure. So as you can see that on x-axis we have pressure drop in psi per 100 feet, and on the y-axis we have demand in the GPM, gallons per minute. So we know that we know that the demand is 108, and we know that the pressure drop is 2.77 psi per 100 feet. We already calculated here. So 2.77 psi over here and 108 GPM here. So it will be around 2.5 inch pipe size, as you can see over here, 108 GPM and 2.77 psi, that is 2.5 inch pipe size. So that's why we got 2.5 inch pipe size here, A to B section. Then B to C section, again we have how much GPM we have here, 104.5, and pressure loss will be same, 2.77 psi per 100 feet, and GPM is 104. So GPM is 104 over here, and pressure loss will be same, so it's almost same, that is 2.5 inch pipe size. So we have used 2.5 inch pipe size. Now the third one is C to D, C to F, and D to E. We have same GPM, that is 77 GPM, and we know that average friction loss is 2.77 psi per 100 feet. So move back to our chart. 77 GPM is 50, 60, 70, 80. So just over here 77 GPM and 2.77 psi per 100 feet. It will touch somewhere here. So it is in between 2 and 2.5 inches. So for the safe side we are going to select the 2.5 inch instead of 2 inches. So 2.5 inches pipe size for these sections. So now move to the next column, equivalent length of fittings and the hells, A to B, what fittings we have from A to B. So this is the table we have used for the fittings for the cold water pipe section and the hot water pipe sections. So A to B, what fittings do we have? If you move to the drawing, A to B, what fittings do we have? We have 1, 2, 3 gate valves and 1 side branch T. 3 2.5 inch, we already know the size, so that's why 2.5 inches gate valves and 1 2.5 inch side branch T. So this is the side branch T over here, and 3 2.5 inch gate valves. So now we have to get that equivalent length in a feet, pressure loss or equivalent length in a feet for these gate valves, 2.5 inch gate valves. So move back to our tables and charts. This time I'm gonna use 103.3 table. This one, as you can see that this is for the threaded fitting. Since we are using the copper tubing, so we are going to use this table over here. So we know that we have a gate valve. You can see that we have a valve, gate valve over here, and 2.5 inch gate valve, and equivalent length is 1 feet. You can see 1 feet, and we have a side branch T, 2.5 inch side branch T, and its equivalent length is 12 feet. So since we have 3 gate valves, 1 for each, so 3 gate valves, we have 3 feet. 1 2.5 inch side branch T, that is 12 feet, we already calculated. So now from section B to C, as from B to C we have only a straight run T, only one. So one straight run T, 2.5 inches. Move back to our chart. and this is our straight run T, and 2.5 inches. Straight run T is 0.5, equivalent length is 0.5. You can see over here 0.5, so 0.5 over here. Then C to F, then from C to F we have a side branch T. C to F we have a side branch T over here, and only one 2.5 inch side branch T. Size we already calculated before, trial pipe size 2.5 inch side branch T. We already calculated 2.5 inch side branch T, that is 12. We can no need to go and check again. So C to D. Now from C to D, what we have here, one elbow over here, size is same 2.5 inches. So 2.5 inch 90-degree elbow. So we need to get its value from the table. You can see that elbow standard 90-degree, 2.5 inch, and its value is 7 feet. Equivalent length is 7 feet over here. You can see. So 7 feet. Then again from D to E, again we have a side branch T. As you can see over here, the most remote outlet we have side branch T, same 2.5 inch size. 2.5 inch side branch you already calculated, that is 12, so we can use 12 over here. So in the same way, the way I have calculated the friction loss for the fittings and the valves for the cold water, you can do for the hot water pipe sizing, and you can write it over here. So I don't want to make video much longer, that's why I will skip this part. If you have any query, you can ask me in the comment section below. So let's move back over here. So equivalent length of the fittings and the valves now we have to write over here. So A to B section, how much is the equivalent length of the fittings and the valves? As you can see that 3 and 12, so total is 15. Then B to C 0.5, C to F 12, C to D 7, and D to E 12. So 15, 0.5, 7, 12 and 12. We have write all the equivalent lengths in a feet. Now move to the next column, 7, total equivalent length. So now we know that the straight pipe length, and we know the equivalent length of the pipes and the fittings, valves and the fittings. So we need to add both of them. Straight pipe length section A to B is 54, and equivalent length of fittings from section A to B is 15. And we need to express this per 100 feet. So 54 plus 15, that is 69, divided by 100, it will be 0.69. So same way from section C to D is, that is 13 is the straight pipe length, 7 is the equivalent length of the valves and the fitting. So 7 plus 13, that is 20, divided by 100, that is 0.2. So in the same way you have to write all the lengths. So now we have to get the friction loss per 100 feet of trial pipe size. Friction loss per 100 feet of the trial pipe size. Since we know that our calculated GPM is 108, and based on our trial pipe size 2.5 inch, we have to write these values. So 108 GPM and 2.5 inch trial pipe size, we have to write the actual friction loss per 100 feet of the trial pipe size. So 108 GPM, 2.5 inch pipe size. So this is copper L, again same. We know that our calculated GPM is 108 and trial pipe size is 2.5 inch. So 108 must be somewhere here and somewhere here, and trial pipe size 2.5 inch, and go below you will find here. So the friction pressure drop per 100 feet is about 3.2, something like this. 3.2 something like this, you can calculate over here, that is 3.2. So we have to write this 3.2 friction loss per 100 feet on this trial pipe size 2.5 inch, based on this trial pipe size. So next we have 104.5 GPM and trial pipe size is 2.5 inch. 104 and trial pipe size is 2.5, it's same, almost same, just 0.1 before 3.2, that is 3.1. let's say 3.1 is the pressure drop, so 3.1 over here. And the next one, we have C to D, we have 77 GPM and 2.5 inch trial pipe size. So we need to know what is the friction loss. So 77, 60, 70, 80, so it's over here, 2.5 inch, almost here, it's touched 2.5 inch here. If we go below, it's somewhere before 2, maybe 1.85 or 1.9 we can take over here. So 1.9, so same over here, 1.9, 77 GPM, 1.9. So this is the actual friction loss per 100 feet based on our trial pipe size of 2.5 inches. So next column is the friction loss in equivalent length. Friction loss in equivalent length. So now we know that total equivalent length based on our straight length of the pipe and based on our valve and the fittings, and we know that the friction loss per 100 feet based on our trial pipe size. So friction loss in equivalent length will be, we need to multiply column 7 and 8, you will get the friction loss in equivalent length. So 0.69 into 3.2, that is 2.21, and then again we have 0.5. Sorry, this one is by mistake 0.85, it should be 0.085 because we need to add both length, that is 8 plus 0.5, that is 8.5. 8.5 divided by 100, 0.085, so it's by mistake 0.85, it should be 0.085. So equivalent friction loss in equivalent length, there will be 0.085 into 3.1, that is 0.26, and 1.62 into 1.9, 3.078, so 3.08. so this is how you have to write these friction losses in equivalent length for each section. So after that we have to add all these length. So since we know that the length to the most remote outlet is, what are coming in the most remote outlet? A to B, B to C, C to D and D to E. This is not a part of most remote C to F. So A to B, B to C, C to D and D to E. We have to add all these lengths. So A to B, that is 2.21, 2.21 plus, then B to C is 0.26, and then C to D is 0.38, and then C to F, no, we have to take D to E to the most remote outlet, that is 3.08. So 5.93. So as you can see that the friction loss in equivalent length is 5.93 over here for the cold water piping, and we know that the pressure available to overcome pipe friction representing by line J is 9.36. So we need to get the value, we need to subtract this pressure available to overcome pipe friction with this value in the column 9, that is friction loss in equivalent length, that is 9.36 minus 5.93 equal to 3.43. so this is the excess pressure available to overcome friction losses. So as you can see that this is the positive answer. Make sure that this value should always be positive. For proper designing of water supply, hot and cold water, this value should always be positive. So the excess pressure available to overcome pipe friction is 3.43 psi. So this value is positive. If this value is negative or not positive, then what you have to do, you need to change your trial pipe size and perform the calculations once again. So you need to balance this one. This should always be positive to make sure that your design is perfect. So the sizes which we have selected over here, 2.5 inches, all are good. So excess pressure available to overcome pipe friction is 3.43.
So in the same way you have to do pipe sizing for hot water, and you have to check. You can see that 7.99 psi is equivalent loss, friction loss in equivalent length. So if you minus 9.36 pressure available to overcome pipe friction minus this loss, so excess pressure available to overcome pipe friction is 1.37. This is also positive, so that means our selected diameters for the pipes is correct, that is 2.5 inches, 2 inches and 1.5 inches for hot water sizing. So this is how you have to do your water supply pipe sizing. This is as per International Plumbing Code IPC. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe. Thank you. Bye bye.